Buongiorno a tutti, grazie per essere qui con noi. And I am very pleased to be here today for the opening of the AnthroFlor SQS sponsored international symposium. And together with my colleague of the SQS, the subcommission on quaternary stratigraphy. My name is Adele Bertini, and I am a researcher at the Dipartimento di Scienze della Terra di Firenze, but I am also secretary of the SQS, which has as chair Jan Zalesiewicz and vice chairs Martin Ed and Liping Zhu. The SQS has a lot of working groups. They are really very active, and during the last months, during the current year, we have very positive interaction with the working group on working on Anthropocene, and especially with its chair and secretary, Colin Waters, and Simon Turner. So together we work and we prepare this symposium. Sorry, I am not sure that I close here. There was a link, sorry. Please, can you? Sorry for this inconvenience. I need to click here. So we work a lot, and we prepare a meeting which allow us to have 2 days full immersion on the Anthropocene issues. We have more than 20 invited presentations, including both lectures and posters. Remember that this evening in the poster section, we will have a meeting coordinated by Simon Turner. The symposium is clear, is free, but and very Spartan and informal, and perhaps it also has the character to be eco-sustainable. We try the link with all the available speakers during these days. If there will be some problems, we can use the time for additional discussion. So I think that we have the possibility to open discussion during the section, but also during the associated social events. This evening, thanks to Andrea Savorelli, we visit the very close Geological and Paleontological Museum. Tomorrow, with the palynological group, the young researcher working with me, we will visit the Orto Botanico, and at the end we will have also a little aperitivo. And on Saturday, thanks to the collaboration of my colleague Marco Benvenuti, a sedimentologist of my department, we will have the chance to visit from a geological point of view the city of Florence. So I think that it is important to express our gratitude to the speakers for having accepted our invitation, but also to all participants, some in presence, but the other on WebEx or in streamings. to the University of Florence, and especially to the president and colleagues of the Natural History Museum. I think that it will be important to remember that the main aim of the AnthroFlor Symposium is to bring the participant more closely into the discussion on the Anthropocene. And also that through this symposium, we would like to engage all of you in open and constructive dialogue. This is very, very important. Today and tomorrow, we will discover that there are different ideas, opinions, but the Anthropocene, however you want to define it over time, exists, and it's not a sarcapone. To discover this strange sarcapone, Italian sarcapone, please look here or ask me. Thank you very much, and then I think that we can start with the scientific section, and it's a pleasure for me to introduce, and I think that
As you want. I'll try from there.
Okay, Professor Colin Waters for the first presentation.
Going on with the presentation, if, for example,
On the introduction and scope of a meeting.
allora la presentazione.
Yeah.
Yes.
Yes. Yeah. So, thank you, Adele. Oops. Good to start. Okay. So thank you very much, Adele. So I just want a few minutes here. My main presentation is the following one, but actually this is just to carry on further with what Adele was saying about what we're going to be talking about over the next 2 days. And that's not moving. Is there, do I need to keep asking you to? Okay. It's not easy to do that because obviously I'm doing the next presentation in particular I need to sort out. Okay. So just to say thank you, Adele, grazie mille for all of your efforts over the last month or so. I know it's taken a lot of time preparing for this. So thank you for, first of all, getting this wonderful venue for us to have this meeting, but all of the coordinating time as well. We much appreciate your time on this. And if you go to the next slide, please. So really the impetus of this meeting, and this is a publication I'll refer to several times today. It's the Geological Society of London special publication, which was published in 2014. We asked a number of people to provide chapters, of which Stan Finney, who was ICS chair at the time, provided a very useful paper which sort of set the scene as to what we needed to be doing as a working group to try and formalize the Anthropocene. And there's a quote which comes from that paper. I'll read it to you. It's, when a task group's proposal is considered by the voting members of the subcommission, there must be an extended opportunity for discussion in open meetings, via the internet or both, and opinions from geoscientists outside of the subcommission should also be welcome and given careful consideration. It is necessary that all points are presented, and all points are challenged, and all questions raised, and all positions stated in these discussions. In such a fashion, voting members become fully informed. Okay, so, so it's that, not that. So anyway, so on that basis, the objectives for today and tomorrow's meetings is to bring SQS members and related interested parties more closely into the discussion on the Anthropocene and its proposed formalization. It's also to help familiarization with and feedback on the latest data being produced by the Anthropocene Working Group, to discuss the general concept of a formalized Anthropocene and its implications, both for chronostratigraphy and more widely, and the results of ongoing analysis of the 12 candidate stratotypes for the Anthropocene, and also discussion of alternative approaches to formalized Anthropocene. So the program for day one today is largely driven by the members of the Anthropocene Working Group. I'll give an introductory presentation following this, just to explain the background for the Anthropocene concept. And then the second session today, after coffee break, is a number of online presentations from members of the working group looking at some of the key markers which provide very high resolution stratigraphy. So we'll look at radionuclides, and there'll be Andy Cundy, particularly presenting on plutonium and radiocarbon fallout signals. Neil Rose will give a presentation on combustion products, so that's the burning of fossil fuels. And then finally, Mark Williams will give a presentation on the paleontology of the Anthropocene, so looking at extinctions, translocations, and domestications of species. And then after lunch, we'll have this visit around the Natural History Museum that Adele mentioned for an hour, and that'll be guided by Andrea Savarelli, who's the curator of the museum, and some spectacular vertebrate fossil collections to be visited. And after that, the afternoon session will largely concentrate on presentations of 6 of the GSSP sites. So we'll have online presentations from Mikakue on the Beppu site, which is in Japan. And then Jerome Kaiser and Juliana Ivar de Sol will give presentations on the East Scotland Basin, so the Baltic Sea. Then the first of the presentations, which will be actually from someone attending, Francine McCarthy will give a presentation on the Crawford Lake site in Canada. And also Barbara Fialkowicz-Koziel will give a presentation on the Śnieżka Pit in Poland. And then finally, Christine DeLong will give a presentation on 2 of the sites. These are both corals, one from the Flinders Reef in Australia, and her own site, which is the West Flower Garden Bank Reef in the Gulf of Mexico. After the coffee break, we'll then have a presentation from Jai Savitsky on the modification of fluviodeltaic systems in the Anthropocene. And then finally, we'll have time to go to the Sala Strozzi and have a look at a number of the poster presentations. So Simon will give a review of each of the sites, except for those who are actually attending, so Francie and Barbara, if they can talk to your presentations, but otherwise Simon will give a review of the contents of the posters and then just open discussion about some of the work that's been done at the sites. So these are just a selection of the 12. We couldn't invite everybody here. Again, it's an opportunity to ask questions about those who were unable to attend today. And then tomorrow, we'll start with a recap and scope for the day from Jan Zalazevich and from Martin Head. And then a number of, really the focus for tomorrow is more of an open debate. So it's sort of questioning some of the reasoning behind the work that we're doing with the Anthropocene Working Group and giving other people an opportunity to present their opinions. We'll start off with the evidence for and implications of determination of the Holocene, and a linked presentation, which is from Martin Head, on the linking of the Anthropocene with the Great Acceleration. So those 2 presentations are sort of complementary. We'll have a half an hour period to discuss the content of those presentations. And then after the coffee break, we'll have 2 presentations from people from the University of Florence. So evidence for early effects of Homo sapiens on terrestrial biodiversity from Guido Gialazzi. And then the geological footprint of Pisa and Firenze, the flood hazard perspective from Marco Benvenuti, who's the person who's giving the field trip on the Saturday. So it's almost an advanced description of what we're going to see, hopefully, on Saturday. And then the afternoon session, presentations from Earl Ellis, is in effect the early transformation, the early Anthropocene concept. And then there's a sort of a for and against discussion with regards to a recent set of publications by Phil Gibbard et al. On the Anthropocene as an event. And obviously there are a series of papers on this at present, and also contrary presentations by members of the working group. And then we'll have, again, two short presentations, one from Lucy Edwards on arguments against formalization, and then one from Jan Zalazevich on arguments in favor of formalization. And then really the rest of the day is an open session to discuss some of the content of the presentations we've heard already in the 2 days, but also an opportunity, particularly for SQS members, to express their general feelings with regard to the concept of the Anthropocene, what their concerns are, what questions they may have about the work that's being done, and discuss how we progress this work as we go into next year. And then we'll finish off with just a half an hour of a sort of a summary of the events of the 2 days. The end of the day on Friday, we'll have a chance to go and visit the University Botanical Gardens, which again are just very nearby. And then, as mentioned, on the Saturday morning, we have, thanks to Marco Benvenuti, an opportunity to see the evidence of the geological Anthropocene in Florence. So that's all I'd like to say with regard to the introduction. So if it's possible to go, if that's okay, to the next presentation. That's right, yeah. Okay. It's working now. Okay, so for the introduction, the contents, a very brief introduction to the history of research of the Anthropocene concept. I'll spend some time talking about some of the AWG outputs and a couple of the voting procedures that we followed. A short section on some of the proposals for the onset of the Anthropocene, the timing of the Anthropocene that we discussed certainly in the early few years of our existence, before we fixed upon the mid-20th century. We'll talk about some of the key markers of that mid-20th century boundary. I'll discuss the ongoing work on the candidate GSSP sites. But to start off with, just to talk about the history of the Anthropocene, clearly there's been lots of work prior to 2000 which has described what in effect are significant human impacts upon the planet. But generally those were in the concept of a Holocene impact of humanity. It wasn't really until Paul Crutzen, who's a Nobel laureate atmospheric chemist, who in 2000 at a meeting of the International Geosphere and Biosphere Program in Cuernavaca in Mexico, was becoming infuriated by this ongoing discussion about the fact that we were living in the Holocene, and stood up and said, well, no, we're not. We're living in, and apparently just picked the term Anthropocene out of the air. That raised a lot of discussion throughout the rest of the meeting, and Paul was asked to maybe produce a paper describing his concept of the Anthropocene. And that came out co-authored by Eugene Sturmer, who independently had coined the term, had been using it informally, had never published it, but Eugene is a North American limnologist, had been teaching his students this term. So the two of them combined to write this paper. They've never met, never did meet, but the paper was published in 2000. And I suppose this is a critical sentence here. It seems appropriate to assign the term Anthropocene to the present, in many ways, human-dominated geological epoch, supplementing the Holocene, the warm period of the past 10 to 12 millennia. So the key thing here is that even though it was in discussion amongst Earth system scientists at the time, their vision of this was very much as a geological epoch. So they'd decided what they thought was the rank, that it was certainly a geological feature, and that there may be now some trying to interpret what's meant by supplementing, but clearly in Paul's vision, this was to follow a termination of the Holocene, so it replaces, in effect, that the modern succession is now part of the Anthropocene. Part of the problem perhaps comes from this title, The Geology of Mankind, and you also see reference to the ages of man, or the ages of humans. And it gives us the impression that the Anthropocene that's mentioned here represents all of the geology of mankind. And clearly, this is not true with regards to the understanding that Paul Crutzen had, because humans have been impacting the planet for 300,000 years. This is specifically talking about something that's quite recent. And then in 2002, a follow-up paper by Paul in Nature aligned the Anthropocene with the start of the Industrial Revolution in Western Europe during the late 18th century. And the quote is, when analyses of air trapped in polar ice showed the beginning of growing global concentrations of carbon dioxide and methane. So he's attaching it very much with a particular event. In fact, he suggested possibility of the invention of Watt's steam engine in 1784 as being a specific event to represent the start of the Anthropocene. Probably the next key development is this publication, which is led by Will Steffen, but also include Paul Crutzen and John McNeill. And it's the introduction of this concept of the Great Acceleration. Their use of this term was as a potential second stage of the Anthropocene. So they recognized around about 1950 an acceleration in a number of signals, and they thought that this was a significant event within the Anthropocene. If you assume the Anthropocene started the Industrial Revolution, this was a next stage on. And this is something that Martin, in your presentation tomorrow, will be discussing in more detail. But just to give you an overview, there was a follow-up paper. Right, so that stopped working again. Yeah, so a follow-up paper by Will Steffen et al. In 2015 basically takes the data sets on, but it's essentially the same format. So it recognizes a series of socio-economic trends. So these include things like increases, very marked increases around about 1950 in population, urban population, the amount of primary energy use, production of fertilizers, water use, production of large dams. So all of these show very marked inflections around about 1950. These represent socio-economic trends, which can then feed into the Earth system trends, which are also showing significant upturns around about 1950. So things like carbon dioxide, nitrous oxide, methane, ocean acidification, nitrogen to the coastal zone, all of them show, and terrestrial biosphere degradation, all of them show marked inflections around about 1950. The two at the bottom left, which is tropical forest loss and domesticated land use, don't show that same system, but at least the data sets here are largely showing a significant modification, an inflection around about 1950, which is this concept that there's a global impact and a series of Earth system trends are being modified significantly around about this time. The idea of an Anthropocene as a geological or a stratigraphic unit really didn't get discussed until 2008 in a publication in GSA Today. It was led by Jan Zalazevich. At the time, he was chair of the Stratigraphy Commission of the Geological Society of London. I was secretary, and still am, in fact. Phil Gibbard was also a member, and still is. And the group produced this paper in 2008. It's a fairly short presentation, and in the end, didn't greatly disagree with the work of Paul Crutzen. but at least it was an opportunity for geologists to talk about this, and as a result, it became perhaps more widely known within geological circles, at least. And as a repercussion of this, Phil Gibbard, who was SQS chair at the time, invited Jan to set up an Anthropocene working group in 2009. And Jan Zalicevic and Mark Williams were both chair and secretary of the working group in its initial years. Jan continued through to 2020. Mark was replaced in 2011 by myself, and through till 2020 as secretary. Now, clearly, when we've got a topic such as the Anthropocene, we need more than just stratigraphers, at least to discuss the narrative of what the Anthropocene represents. At that early stage, we were talking about whether we even thought there was any justification in this term. So we needed to have people outside of the stratigraphic community. And the 36 members at the time ranged in background from both geology, archaeology, history, social science, ecology, oceanography, glaciology, atmospheric chemistry, and international law as well. So a very diverse community, all of who were able to provide input in our formulating an understanding of what the Anthropocene really represented. Then at the end of the sort of 8-year cycle, Jan came on to become chair of SQS. I was asked to then become chair of the working group, and then Simon joined as well as secretary. And as part of this new executive, we were also really given steer by ICS to say that, first of all, the working group was too large, and also they had some degree of discomfort, the number of non-stratigraphers involved in the voting process for this potential GSSP. So we were not happy about removing membership. People who'd been involved right through from the beginning, 2009. We wanted to carry on being members of the working group. So we decided to split the group into voting members whose only distinctive responsibility was voting on the GSSP proposal. And these would be the expert stratigraphers. And we did invite some extra people onto the group at this time, partly those who were responsible for working on some of the sites, but also those responsible for looking at some of the key markers. And so they were considered as voting members, and everyone else, as non-voting members, were contributing fully throughout the rest of the debate. We've been fortunate through our time to be able to have lots of meetings like this. Our very first one was in Berlin in 2014 at the Haus der Kulturen der Welt. So that's the picture on the bottom right. We've met twice more formally in Berlin last year and this year, specifically looking at the GSSP proposals, partly because the HKV in the end have provided financial support for carrying out some of this work. So they have an interest in recording the process that we're undertaking to actually make this decision. We've also met in Cambridge in 2015 at the MacDonald Institute for Archaeology at Cambridge University, so where a lot of the discussion at that time was looking at the sort of early human involvement in modification of Earth systems. The Oslo meeting in 2016 was timed just before the IGC meeting in Cape Town. And it was an opportunity for us to discuss, first of all, a voting process I'll talk about later, which we did in advance of IGC to report where we were with regard to our deliberations. We also met in Mainz in 2018. This is at the Max Planck Institute for Chemistry, which is Paul Crutzen's home institute. And we were very fortunate that Paul was able to attend, despite failing health, both of the days and contributed greatly to our discussions. And then our one meeting outside of Europe was in New Orleans in 2019. And this was the end of a year program that HKV were involved with, analyzing the impact of humans along the Mississippi catchment area. We've been responsible for a large number of publications over the last 13 years or so. Some of the key summary thematic sets of papers were produced in the Philosophical Transactions of the Royal Society in 2011, led by Mark Williams as the main editor. I've mentioned already, and will mention several times, this stratigraphical basis for the Anthropocene, which I was the lead editor for, a number of key papers in that. And it was really that set of thematic papers where we started to get more of a guidance towards the mid-20th century as being the key level for recognizing the onset of the Anthropocene. And then, almost as a summary of that first decade of our analysis, is this book led by Jan Zalewicz, but authored by many of the members of the working group. And this really summarizes all of our thoughts over our sort of discussion of the narrative of what the Anthropocene represents. And it represented the end of that stage of work before we then move on to looking at analyzing the GSSP candidates. So I mentioned about this non-binding indicative vote that we had in 2016 in advance of the IGC in Cape Town. This then became published in this paper led by Jan, published in 2017. And this was really just to have clarity within our minds as a group what we felt the Anthropocene represented. So a series of questions. Is the Anthropocene stratigraphically real? So 35 votes, 34 in favor. So 97% in favor of recognizing the Anthropocene as a stratigraphically real unit. Should the Anthropocene be formalized? 83%, 29 voted in favor for that. So strong endorsement. The hierarchical level of the Anthropocene. Now here there's quite a large number of alternatives. Still 59% were in favor of the series or epoch level. So this is the one that's guided by initially Paul Crutzen's proposals, but also the name itself lends itself to being considered to be of series level. As many, if not more, thought it should have been higher rank than that, so either system or ERFM, as for should it be a lower stage or subseries. But we had quite a large number of abstains and uncertains as well. But clearly, the dominant feature there was to recognize this as epoch level. Base, or the beginning of the Anthropocene, suggestions include, again, a number of alternatives. I'll talk about these in a bit more detail later, but 81% thought that somewhere around about the mid-20th century was the most suitable time. We had some earlier suggestions linked to Roman lead signals 3,000 years ago, and also that the peak radionuclide signal in 1964 was one of the options, but dominantly 81% thought the mid-20th century was most suitable. But you'll notice also a number were recognizing a diachronous informal unit as a possibility, and that's something we'll be discussing tomorrow with regard to what became evolved into Phil Gibbard et al.'s event papers. GSSA or GSSP. Majority, 73%, thought that we should be aiming for a GSSP rather than a GSSA. Some degree of uncertainty on that as well, but the majority opinion is to seek and choose a candidate GSSP, as this is the most familiar and widely accepted method of defining geological time units. What is the primary signal? Now, again, we had lots of choices here, and of course, we also had a membership that had specific backgrounds, which may lead to them voting for their own favorite signal. But there's still a dominance towards the radionuclides. The plutonium and radiocarbon got about 40% of the votes. But also, there was interest in plastics, fuel ash, CO2 concentrations, stable carbon isotopes, and also then just the various things like lead, persistent organic pollutants, and technofossils. So there's a broad range here. And it wasn't a strong endorsement necessarily for the radionuclide fallout. So at this stage, we still didn't want to pin ourselves down to one particular primary signal, but recognizing that these represented a whole host of signals around about 1950. As we came towards that sort of 10-year period of review of where we were, it was felt necessary that we had a formal binding vote. which we had in May 2019. This was much more honed down to two very simple questions. First of all, should the Anthropocene be treated as a formal chronostratigraphic unit defined by a GSSP, and should the primary guide for the base of the Anthropocene be one of the stratigraphic signals around the mid-20th century of the Common Era? So those signals I've just mentioned. And in both cases, 29 voted in favour, which is 88% of the voting cast, and 4 voted against, no abstentions. So again, strong endorsement for both of the proposals put forward. So this represents now our viewpoint going forward, looking into then defining the GSSPs as the subsequent phase of our work. So when did the Anthropocene commence? This was really some of the debates that we had in that first 5 years of our existence, looking at some of the proposals being put forward in publications and trying to decide where our preferred level would be. So the first one is the suggestion that around about 13,800 BP, so this is the late Pleistocene megafaunal predation and vegetation changes associated with the late Quaternary extinction. So a paper by Doughty et al. In 2010 had put forward this specific date. Then there's also at 11,000 to 9,000 BP, the emergence of significant human niche construction. So this is extension of urbanization, agriculture and pastoralism across the planet. And a proposal by Smith and Zeder in 2013, in effect to say the Anthropocene is the same as the Holocene, and in fact, could we even replace the Holocene by this new term? So we then jump to the next proposal, which is the Orbis spike, which is a 10 parts per million dip in the atmospheric CO2, which was proposed by Lewis and Maslin in 2015, partly because it had a link with the sort of Columbian exchange of species and also had a more social science respect with regard to colonialism as well. Then there's the original Paul Crutzen suggestion of the start of the Industrial Revolution. Then we have a specific date, 16th of July, 1945, which was put forward as the destination of the first nuclear bomb at Alamogordo in USA, which was proposed by Zalazevich et al. In 2015 as a GSSA. But saying that, this one event does not represent a large global signature within the geological record. Then we have the Great Acceleration, 1950, as a general significant change to both socioeconomic and geological signatures. And so just a general mid-20th century was put forward as a potential start for the Anthropocene. Or more specifically, if we then look at something like the plutonium record, specifically plutonium-239, there's a significant change around about 1952 with regard to the first hydrogen bombs, the thermonuclear devices that started in 1952, but providing a much more globally distributed plutonium signal compared with those first atomic bombs in 1945. So this was proposed as a more refined potential start for the Anthropocene. And then another proposal in 1964 is the peak of the bomb spike, which was put forward by Lewis and Maslin in 2015. So it's just at the point where we've seen maximum detonations before we have the introduction of the Partial Test Ban Treaty in 1963. So the problem with this is it obviously postdates a lot of the signals we see as part of the Great Acceleration, and also to some degree the bomb spike is more diachronous than the start of the signal. And finally, a proposal for none of the above, so that the Anthropocene represents a diachronous unit that reflects all anthropogenic impact, and as such should be an informal, non-chronostratigraphic unit. So let's just review some of those in a bit more detail. So let's look at this first 13,800 BP date, and really the veracity of picking a specific date for the late Quaternary extinction. So the idea is that the extinctions are in part driven by the first incoming of Homo sapiens into a particular area. And the upper figure, just to give you an idea of some of the dates at which point Homo sapiens moved into parts of the planet, starting at one in Africa at 300,000 years and spending a large part of the next 200,000 years, largely based in Africa, gradually spreading out across Europe, eventually getting to Australasia by about 56,000 years, Northern Europe and Eastern Asia over the next few tens of thousands of years, not getting into America until 14,000 years ago, and then concentrating into moving into new areas, the island areas such as Caribbean, Madagascar, New Zealand, Hawaii, etc. So there's a great diachronicity in the movement of Homo sapiens across the planet. So this idea that 13,800 years is essentially a date that's more relevant to the Americas than anywhere else. It's not a global date in any respect. And the lower figure, which is a new one we produced, which is looking at the number of extinctions per million species per year, this E over MSY, just to try and characterize how many species we're talking about for mammals in particular. And it's clear from this that the early extinction rates we're seeing, particularly for that interval between 50,000 years and 8,000 years, though elevated compared with background, is still quite small. Even the terminal late Quaternary extinctions between 15,000 and 8,000 years, though significantly raised, are much smaller than those related to the extinctions associated with the movements of humans into the island areas in the last 1,000 years or so, and certainly greatly reduced compared with those we're seeing since the Columbian exchange over the last 500 years, and specifically during the Anthropocene, where we're looking at much more elevated extinction rates, and involving more in the way of smaller species of mammals as well, not just the megafauna. So the idea of a 13,800 BP date has no global significance, really. Then there's this concept of the Anthropocene equating to the Holocene, so linking it to emergence of significant human niche construction. And this figure, originally from Stevens et al. In 2019, but reproduced by the Phil-Gibbard et al. Paper in 2021, really does show that the idea that particularly agriculture and pastoralism at that time is really just a feature of the Middle East. So the sort of the cradle of civilization, but the timing is very diachronous. So as a Holocene concept, these things do show a very gradual distribution across the planet. There's no one particular date where neither of these features, and urbanism as well, represents a specific signal that you can pick to start the Anthropocene. There was another proposal by Bill Ruderman looking at greenhouse gas emissions, and what he was recognizing was that the blue curves represent what you would expect to be seeing both for carbon dioxide, which is the lower panel, and methane, which is the upper panel, how they would show a typical decrease over time during an interglacial interval. And the red represents what we're seeing currently over the last 10,000 years. So there's a clear upturn both for CO2 around about 7,000 years ago and for methane at about 5,000 years ago. The CO2 was thought to represent protracted deforestation, and the methane relates to the spread of rice cultivation, particularly in East Asia, and also introduction of livestock into Africa and Asia. The CO2 signal perhaps has been argued by many now not to be linked to human interaction with the planet, but they think the methane one has more strong arguments in favor of it being anthropogenic in origin. But what this figure doesn't do is explain that the zero here is not the present day. It's essentially the end of the pre-industrial period. And if you now put in where we are with CO2 at 415 parts per million and methane at 1890 parts per billion, clearly there's a large part of the present day that's missing from this figure. And that's really illustrated in this figure here, which is for CO2, where the Ruderman figure basically stops at the last of the black squares, and all of that rest of the change is the black line that carries on up to the present day. This figure is used to illustrate this orbit spike feature that the Lewis and Maslin paper suggested should be the start of the Anthropocene. And it's just a 10 part per million dip in atmospheric CO2. So it's only recorded in ice core. This is not a signal that you can find in any other geological archive. And really, it sits well within that 800,000 year CO2 range. There's nothing specifically significant about this compared with what happens subsequently from 1800 onwards with this very prominent change in CO2. But also importantly, it's not just the CO2 signal that you see changing. The orange curve there is showing that the stable carbon isotopes show a very marked decrease, initially starting around about 1800 with a 0.5 per mil decrease, but a very significant ramping down to about a 1.5 per mil decrease over the time of the Anthropocene, or the last 70 years or so. So it's comparing small features which are not particularly marked compared with the bigger features that we're seeing at present. It means that we really didn't feel that the Olbis spike represented something that was greatly significant for a start of the Anthropocene. Then there was this idea of the start of the Industrial Revolution, which was initially the view of Paul Crutzen, but also the Zalazevich et al. Paper in 2008. And it represents the initial changes to carbon and nitrogen cycles. It broadly represents this end of the Northern Hemisphere Little Ice Age around about 1850. You could pick the Tambora eruption as an isochrosine event around about 1815 to define the base, but that's not an anthropogenic signal. In the end, we decided that really we're looking here at something that was a very Western European or even UK-centric viewpoint. And even there was diachroneity in the signals, and so 1800 in the UK would represent, say, 1850 or later in America, North America, and much later as you go into Asia. So there wasn't a specific time here that we could pick. And the idea of recognizing what steam engine's invention in a geological record was impossible. So the idea of fixing an historical event to a geological one really didn't work in the case of the Industrial Revolution. Now, the GSSA proposal that came from Jan Zalazevich et al. Was guided again by this Finney paper in the Jolsock of London's special publication. The paper by Finney said that a GSSA would be very accurate in contrast to the numerical age calibrated for a GSSP. So we took that as a guidance to say, well, a GSSA would be a suitable way of defining the Anthropocene. And so this paper in Quaternary International that Jan led suggested the Anthropocene could be defined as a GSSA, a point in time of the human calendar, and that we propose an appropriate boundary level here to be the time of the first nuclear bomb explosion in Alamogordo, New Mexico, on the 16th of July, 1945. We were then given guidance by ICS to say that they really wouldn't, rather that we didn't pick a GSSA, because that would be very much against the whole procedures that ICS were following to try and get as much of the geological timescale classified using GSSPs. So our whole focus then moved towards defining a GSSP. And just to summarize the key signals that we've been using, so novel materials, so that's novel mineral-like compounds, aluminium, concrete, plastics, and fly ash. Particularly, I picked that out because Neil Rose will give a presentation later on that topic. Geochemical signals, so the carbon and nitrogen cycles, climate change, heavy metals, organic chemicals, and radiogenic fallout, which Andy Cundy will present on. Biological signals, which Mark Williams will present on the extinctions, species invasions, and domestications. And I will look again in more detail at some of these in a presentation tomorrow on the evidence for and implications of the termination of the Holocene. So perhaps the key paper here, and the one that's the working group's most cited publication, is this one in Science, published in 2016. And just to summarize, so the content of this is essentially two figures represent the summary of the evidence. And it's looking at a number of mostly ice core records of atmospheric concentrations over the last 12,000 years to show how significant the impact has been over the last 70 or so years. In the case of the nitrates, we have a doubling of reactive nitrogen, potentially the greatest perturbation of nitrogen for the last 2.5 billion years. We have temperature changes of a 1 degree since 1970 at a rate 170 times the rate over the last 7,000 years, but in the opposite direction, so a very clear change, and one that's now been proposed to say that we're now at temperatures that are greater than those at the Holocene thermal maximum about 7,000 years ago. In carbon dioxide, we're now 125 parts per million greater than at the start of the Industrial Revolution, and it's rising at a rate that's 100 times faster than at the Pleistocene-Holocene transition. And for methane, now at 1859 parts per billion, in 2017 it was at least, that's 257% of the pre-industrial levels. So just looking at the profiles, we have, to some degree, a plateau or a leveling of a lot of the signals until we get to the last couple of centuries when we suddenly see this marked inflection and a spike on the right-hand side of the figures. And we just felt that that was very difficult to consider those signals on the right-hand side to be still part of the Holocene, particularly when you look at the various, the 3 stages of the Holocene, where there's very little perturbation at any of these signals at that time. And even at the start of the Holocene, in many cases, the signals are more reduced or at a slower scale than they're seen at present day. So this was the argument we were using to say at least we should be seeing the Anthropocene at epoch level. And then looking more detailed at some of the novel signatures, and we have, first of all, at the bottom, global black carbon, total concentrations. This is a production figure, and so small amounts of biofuels up until about 1875, supplemented then by emissions from coal burning, and then supplemented from 1950s onwards by this increase by diesel to the production of about 6 billion tons of black carbon per year. Production figures for plastics and concrete, so we've got about 500 billion tons of concrete and 8 billion tons of plastic produced since 1950. And then the radiogenic signals, so the bomb spike saw a doubling of radiocarbon signal in the atmosphere, and then also a pronounced 1952 start to the plutonium signal. Now, having decided we'd go down the process of selecting a GSSP candidate, we had to then understand where would be the most suitable place to look for for GSSP. So we then did this research, which was published in Earth Science Reviews in 2018. And it essentially recognized quite a number of different environments. So a marine environment, broadly, certainly at abyssal depths, accumulation rates are too small. In shallower waters, there's too much disturbance by things like trawler fishing and bioturbation. So we had to home in on marine anoxic basins where these weren't issues. But also, we recognized that corals represent a potential good marine signal for the Anthropocene. In that transition between marine and terrestrial, we have estuaries and deltas representing potential location for finding our GSSP. In the terrestrial setting, lakes, tree rings, glacial ice, and raised peat bogs and anthropogenic deposits all had potential. Of those, the only one we didn't then put forward as a proposal was tree rings. We never found a group prepared to do the work on this. And then the subterranean setting, anthropogenic deposits and speleothems representing potential candidates. So the ones shown with asterisks are one where we have good reason for recognizing annual or even seasonal layering within the successions, which added that extra degree of fine resolution to the successions. So now going to the sites that are being considered. And this really came from a funding opportunity that the Haus der Kultur und der Welt came to us in 2019, saying that they had some funding to allow us to really proceed the whole potential of analysing GSSPs. We'd got several sites that had already done work and had published, which represented potential candidates. There were several sites where there was lots of great data, but they'd only honed in on certain signals. And what we were looking for was really to try and get a multi-proxy analysis for each site, so there was consistency and allowed greater correlation between the sites. And what this funding allowed us to do was to take those projects and provide a little extra money for them to do this initial, to do the extra bit of analysis that helped sort of provide a broad suite of analytical data. And then some of the sites have been separate to this procedure altogether. So particularly the Beppu Bay and the Vienna sites have been entirely self-funded. So just to summarize, there are 12 sites being considered in 8 different environments across 5 different continents. And this figure, which appeared in the episode paper that Martin led on, it was dated October 2021, so it's now obviously advanced there. Hopefully a lot more in the way of green signals here. These represent the different analyses being carried out by each of the 12 sites. So all we're trying to do very high resolution scans of the core. All of them are in core with the exception of the Vienna site, which is a section next to the Karlsplatz Museum. Many of them have done lead-210 dating. Many of them also, in fact, most of them have done radionuclides assessment, so cesium, americium, plutonium isotopes, radiocarbon. A lot of them have done lead isotope work, carbon and nitrogen stable isotopes, fly ash analysis, sometimes in quite novel environments where they've not been investigated previously. We looked at heavy metals and mercury, microplastics in a small number of the sites, organic pollutants, black carbon, and then more niche proxies for in certain specific environments, such as oxygen isotopes and boron isotopes, looking at paleotemperatures and paleo pH values. Then the CO2 analyses as well has been carried out, particularly in the ice record and speleothems. And paleontological data as well, so mainly looking at microfossils, so diatoms, foraminifera, ostracods, pollen, zooplankton, and also mollusks being carried out in the San Francisco Bay. So the idea here was, rather than specifically picking one primary marker, what we were still trying to do here was to show the demonstration that the Anthropocene represents a change to many different proxies for the Anthropocene. Many different signals are changing very dramatically at this time, and we wanted to demonstrate that the Anthropocene had reality because of those changes, not just because we had one specific marker that clearly represented that base. And this is sort of just the latest summary of where we are with the sites. And in fact, it's slightly out of date, and I think Beppu Bay has changed slightly with regard to some of the levels here. But what it shows is first of all, the age range of the core for each of the sites. But then the bands that you're seeing here represent the ranges from the onset through to peak for just 4 of the markers. So it's the fuel ash, the SCPs, the plutonium, we've got the radiocarbon, and stable nitrogen isotopes in that order. And what you'll see as a general feeling here is that there's a range of several decades between onset and peak signals. But if you consider where we have the rapid changes, this is this sort of great acceleration in curve, well, that actually is much more consistent. So if you look at the boxes here, the boxes, the circles, the ends, and the triangles, they're around about this level of 1950. And particularly the radionuclides, almost all within that sort of year or two range of 1950. So the implications, what we're proposing in effect is that the Holocene has been terminated by the Anthropocene. It would require that if we propose a GSSP, that the chosen site will then provide the name of the stage or age. So that, as yet, is unnamed. But the clear thing here is the Megalaean and the Holocene would be terminated by this new geological time unit. So to summarize, Paul Crutzen's concept of an Anthropocene was of an epoch terminating the Holocene and starting at a notional onset of the Industrial Revolution. Over the last 11,000 years, strata show increasing but gradual human modification of landscapes, geochemical signals, and biodiversity. This is all consistent with variation within the Holocene. There's been substantial and approximately global synchronous changes to the Earth system, including novel materials, intensified dramatically at the mid-20th century during the Great Acceleration, which is our preferred start for the Anthropocene. The AWG, following extensive investigations, has settled on an Anthropocene as a series or epoch level commencing in the mid-20th century and to be defined by a GSSP. And the AWG is coordinating the investigation of 12 sites with multi-proxy approach of investigation to demonstrate high-resolution correlations between the sites, not just as a primary marker. And that these sites span 5 continents and 8 different depositional environments, reflecting a truly global correlation. So I'll finish with that. Thank you. Do we have time for questions? Are we getting close to coffee time?
Are there any questions here, but also from participants on online? No questions? Yes, Silvia, can you, perhaps it's better if you come here.
But actually, do you want to take the mic?
Oh,
Take the mic.
Oh, there's a microphone.
Oh, you can.
we have the microphone.
Oh, thanks a lot for the presentation, for the overview. It was great. My question is probably too much preliminary and is really like a curiosity. What is the link between defining the Anthropocene and the role that we have in society as a scientist and as a geologist in kind of defining the Anthropocene and kind of having a role in saying, okay, humans modifying the environment in somewhere that if we define a GSSP, it means it is geological consistent and it can be like a millennial or something like this.
Yeah.
This could be kind of defined and seen by everybody.
Yeah, I suppose there's perhaps 2 competing proposals here. One is to say that humans have always been impacting the planet and have been doing so gradually with time, and that we're now just at one phase within that gradual change. And nothing specifically great has happened in recent decades, as opposed to another concept, which is by saying that the Anthropocene can be picked by very dramatic changes around about 1950, says that there are people in this room who've lived through the entirety of that change, and it's been very, very brief and very abrupt. And that says something about what we are capable of doing now at the levels of development we have, the levels of consumerism, of global trade, all have this significant impact. And in many of these signals, they will continue rising or at best will plateau. Some of them are irreversible. The biotic changes that we're responsible for cannot be reversed. So we're saying that rather than being just part of a continuum of the Holocene and no great change, that what we're seeing is a transition to a new Earth state, and one that we can't go back to the Holocene. And it has a very different mindset if you think about it in that way. Okay.
Thank you.
We have also a question from Lucy Edwards. She is online, so please, Lucy. It is, sorry, We have some problem with the... Yes, try again.
Qui sì, però siete lì.
Sorry. Try again. Okay. Can you hear me? Yes, now yes. But
Yes, I can hear. It was a mistake. Sorry, I haven't a question.
Okay, let me start. I was absolutely fascinated by the slide that had the 12 candidate GSSPs, where the vertical axis was dates. How good are the age models, and where are they from? If you know the age,
Right, so
it's like you've already answered the question.
clearly I can't go into that detail in that slide, but each of those sites is being published in a separate presentation, in an article, in a thematic set of papers in the Anthropocene Review. They're currently in the process of review with the aim of publishing this autumn in advance of our voting. So all of the models, the chronologies are described in great detail. Obviously, with the annually and seasonally layered successions, we are talking about very high resolution models.
Lucy, if you like, you can... No.
I think,
No
obviously,
more questions.
We're going to have presentations by some of the six of the sites later on.
Simone?
And obviously they have the posters as well. So the chronology information might come out from just those presentations in detail.
So, please, Simone.
Hello, thank you for the presentation. My question was about the proposal of setting the Anthropocene like an epoch and not like a stage of Holocene. That's why for the entity of the Anthropocene like event, or because we think the duration of the Anthropocene is like an epoch standard.
So it was that comparison of taking a number of globally distributed signals and comparing them like for like against the variations you see at the stages within the Holocene and at the start of the Holocene. For many of them, we are talking about changes which are well outside the variation of the Holocene, certainly way outside the variations you see within individual stages, and in some respects of scales of quaternary level changes. So we took a sort of balanced opinion here and saying rather than talking about the level of the quaternary being terminated at this point, we were saying that clearly if you look at the parameters for the definition of the Holocene, we are of that level of variation, certainly much greater change than we're seeing at the stage boundaries.
Yes. We have a question from Emily Coster, please.
I'm trying to... Okay, can you hear me?
Yes.
Yes.
Thank you. I'm hearing an echo in my voice. I'll go ahead. What geology's great gift to the world has been the long view and the big picture. And the Anthropocene as being proposed is of the here and now. And I'm wondering how Colin and others might comment on, which is that if we look into the human future, not even maybe the geological future, the year is 2100, 22 AD. How do you think that society at that point, hopefully guided more than it is today by geological thinking, might look back on the value of the Anthropocene as being defined by mid-20th century atomic bomb tests?
Okay, first response is that a lot of the criticism that we received is that it's thought that we're looking at the summit here that's the future. And what we've been very careful to do all the way along here is to look at this on the basis of the geological evidence. So this is stratigraphy, not projection into the future. So we believe there is enough information in the geological record already to show significant change which warrants it being epoch level. So irrespective of your idea of looking into the future, the evidence is there. But if you then look into the future, first of all, there's lots of evidence to say that modeling would predict that things like the carbon dioxide concentrations will stay elevated for tens of thousands of years, that temperature change will be elevated for that sort of duration of time. Clearly, the biological signals will carry on changing and not be reversible. So these represent those long-term, or if not permanent, changes. How the bomb spike fits into this, clearly, when we're looking at the Earth system as a whole, a lot of the changes that relate to the bigger picture of things like burning fossil fuels, the introduction of nitrogen-based fertilizers, so increasing in agriculture across the planet. So these are the things that are changing the Earth system. The bomb spike does not change that Earth system. What it creates is a very finely resolved boundary. So it's the same as with the Paleogene, the Cretaceous-Paleogene boundary, the KT boundary, that the impact level is the marker, but then the subsequent changes you see in, say, the biological record and the geochemical record that persist throughout the Cenozoic are a result of that one impact feature. And we can use the bomb spike, again, as a clear marker, as a very good correlation tool, but that's not the cause of the Anthropocene.
So may I just supplement, Colin? And there's clearly an abundance of evidence for geological rationale of detecting what you're doing in the mid-20th century. Per my paper last week in Episode, my point of view and my vantage point is that, particularly with respect to views retrospective from future human societies, is that the world is struggling to even identify and relate to its natural environment, and so this echo is being very difficult to speak against. But what I'm getting at is that I think society needs most a geological clarification of the extent with which the human species has altered and controlled the human environment. I'm not disputing the abundance of geological evidence for the mid-20th century start of something, but the human need is to come to terms with the extent of the influence of Homo sapiens as a unique species that, in the view of the International Science Council, has, since 300,000 years ago, started to be the dominant influence on the environment rather than the environment the dominant influence on any life form, including humans. So I'm concerned that geology is an overly restrictive view of its value to the greater good of society.
So obviously, I'm talking in this perspective of the chair of the Anthropocene Working Group, whose task is to try and define this as a geological time unit. So what you're asking is a much wider perspective, and clearly what we're doing has wider social impact, but our clear criteria here is defining a geological time unit. And that's what we're doing, and we see there's clear evidence for that. And that still, in my opinion, has says a lot about how humans are impacting on the planet and how immediate that change is and how it will continue to represent a change into the future. So I'm not sure at what point your comments are contradicting that.
I think that there are no more questions. We can close. We have a break now, and we will be here at 11:30.
Okay, that was a very nice and small coffee, as is traditional. I'd like to introduce now the series of speakers we have lined up to discuss the key markers in high-resolution stratigraphy. They're going to be about 20 minutes presentation time of each, and we have three lined up. We have radionuclides, combustion products, and paleontology of the Anthropocene. And first, we have Andy Cundy from the University of Southampton. He's the research director of GAU Radioanalytical, and he's a professor in the School of Ocean and Earth Sciences and the National Oceanography Centre in Southampton. On a personal level as well, he's a reason why I'm here. He was my PhD supervisor, and we work in Sicily many years ago. And so I hold him partly responsible for the situation we're in now. So Andy, if you can hear me, and if you could start, that would be great.
Brilliant. Thanks, Simon, and apologies for putting you in this position. It sounds like I'm your father in some ways, but no, thanks for the kind introduction, and thanks for the invitation to present today. I've got about 20 minutes, so I'll move through this fairly quickly, but I will apologise actually for not being there in person. I'd love to have been in Florence, but hopefully this online presentation will work well. So as Simon has said, I'm Andy Cundy. I'm from the University of Southampton and the GAU Radioanalytical Laboratories, and what I'd like to present today is a presentation on key markers in very high resolution stratigraphy, radionuclides. So by way of content, I'll start off by talking about a bit of background, radionuclides as potential global markers of the Great Acceleration and the mid-20th century, particularly following detonation of the Ivy Mike thermonuclear device, which you can see at the bottom of the screen there, in 1952 in the Pacific. Then I'll discuss what are the key fallout products forming a stratigraphic signature. And then from the point of view of stratigraphic utility, I want to talk a little bit about distribution of these radionuclides, these anthropogenic radionuclides, their preservation in the geological record, and their ease of measurement. And then I'll move on to a bit of a discussion on temporal resolution and also source fingerprinting. And I'll give some examples from the candidate GSSP sites that the Anthropocene Working Group have been examining. And then I'll conclude. So initially then, just to give a bit of background on radionuclides as potential global markers of the Great Acceleration in the mid-20th century, I think the key thing here is this pulsed input on a global level of anthropogenic radionuclides following the phases of high-yield above-ground thermonuclear weapons testing in the 1950s and 1960s. So the diagram you can see in the middle of the slide there shows a timeline of key events that have influenced anthropogenic radiogenic signatures. This is modified from Waters et al. 2015. And the key point here is that we have early tests and detonations of atomic devices, which effectively give a regional signature. And it's really from 1952, with the onset of high-yield thermonuclear weapons testing, above-ground weapons testing at various locations around the globe, that we start seeing stratospheric injection of fallout products which are globally distributed. So effectively that began with a 10.4 megaton TNT equivalent Ivy Mike test at Enewetak Atoll in the Pacific Ocean on November the 1st, 1952. And then that was the point at which nuclear fallout shifted from being a regional to effectively a global fingerprint of nuclear activities. And we can effectively track on this diagram on the slide there through the plutonium deposition density. It kind of follows the aggregate number of tests. So particularly there was an acceleration of testing in the late 1950s, and then there was a nuclear weapons testing moratorium between 1959 and 1960, and then there was a onset of additional testing, quite large-scale testing, following the signing of a limited test ban treaty by several of the major nuclear powers in 1963. So there was large amounts of testing in 1962 that injected material into the stratosphere, which was effectively globally distributed and returning to Earth in 1963. So there we can see that pulsed input very clearly from the plutonium deposition density in the blue line there, and also, of course, other anthropogenic radionuclides were released during these tests, which I'll discuss in a little while. But particularly here, we've got carbon-14, which is another key indicator. And so that shows, again, this onset, this pickup in 1952 to a maximum in 1963, and then decline thereafter. It's important to note that accidents at nuclear power facilities, such as Chernobyl disaster in 1986 and the Fukushima Daiichi disaster in 2011, and also licensed discharges from nuclear fuel reprocessing complexes, such as Sellafield in the UK and La Hague in France, have also input significant amounts of radioactive products to both the terrestrial and marine environments, as well as into the atmosphere. However, total inputs from each of these sources have typically been less than 1% of that from atmospheric weapons testing. So these are regionally significant inputs, which in some locations overwrite this fallout signature, but they don't form a global marker. So what are the key fallout products forming a stratigraphic signature? Well, the specific fallout products that are released following a nuclear detonation depend on the characteristics of the device detonated and also the nature of the detonation. But generally, you can organize these products into the following three categories based on their mode of generation. So we have fission products produced by the splitting of the uranium or the plutonium atom. Here we've got cesium-137 and iodine-129 as examples. In the diagram on the right of the slide there, you can see barium and krypton as examples as well. A range of these fission products are produced. We also have actinides, which are produced through neutron adsorption during the detonation. So here we have americium-241 and plutonium isotopes. And finally, activation products, which are formed through the interaction of neutrons with the surrounding environment, including the atmosphere, here generating carbon-14. And I've highlighted in bold the ones there that are of primary interest to the AWG as markers for this 1950s mid-20th century point, and also which kind of potentially act as basal markers for this great acceleration phase that has been discussed already. So it's important to note that these are widely used dating tools, particularly cesium-137 and americium-241, and obviously carbon-14. But cesium-137 and americium-241 really provide a first go-to method that a wide range of environmental scientists use to get an idea of the age of modern sediments in a core. And it's also important to note that these fallout products are very widely used in the earth sciences and oceanography and physical geography and the environmental sciences as traces of environmental processes. So, for example, tritium that's produced in nuclear detonations as fallout has been widely used as a groundwater tracing tool and also as an oceanographic tracer in terms of looking at mixing and lifetimes of water masses in the ocean. So the post-fallout behavior of these radionuclides depends on their chemistry and also the characteristics of the environment into which they're deposited. So some are highly mobile, like tritium. Others are more particle reactive, and it's these particle reactive radionuclides that show strong interaction with the sedimentary and biological materials that make up the Earth's stratigraphic record. So, for example, the bomb peak in carbon-14 in 1963 to 64 can be detected in most carbon reservoirs with variable offset, including in peat deposits, soil, wood, coral and bone. And without stealing the thunder from any of the presentations this afternoon, hopefully, this is some data for corals from DeLong et al. I think this was derived from Erka's work, who's online as well. And here we can see very clearly this kind of high-resolution record beginning in 1955, this strong increase in the early 1960s and a peak in 1970. There's a slight offset there from the 1963 fallout maximum. But here we can clearly detect this bomb peak in coral deposits. Also, plutonium isotopes readily associated with clays and organic particles in lake, marine and other settings, and these allow characterization of distinct fallout signatures in marine and lake sediments, ice cores and other media. So again, here's an example from Crawford Lake, which I think we've got a presentation on this afternoon, Francine McCarthy and others. So here we can see a pickup of plutonium-239-240 activity. So we're measuring radioactivity there. A becquerel is 1 atomic disintegration per second. So we're measuring becquerels per gram here. And we can see a pickup in the early 1950s, a kind of shoulder in that profile around about 1958. And again, this could well relate to this decrease in input following a moratorium. And then we see another increase to 1963 and then a decline thereafter. So it's important to point out in terms of the distribution, preservation and ease of measurement and the use of these markers in stratigraphy is that effectively not all latitudes are equal and not all deposits are equal. So this is a really useful diagram, I think, again from Waters et al. 2015. I can say it's a useful diagram because I wasn't involved in that paper. So basically this shows the major tests and discharge events that have taken place as part of the above ground thermonuclear weapons testing, and also we see deliberate detonations there, and also the location of other nuclear power facilities that are discharged into the environment. And I think the key point here is to look at the red line there, which shows global strontium-90 fallout. And so effectively we see a maximum fallout in the northern mid-latitudes. And that's related in part to the locations of tests, but it's also largely related to atmospheric circulation patterns. So here we have effectively a stronger signal in the northern mid-latitudes, but we do still have a global signal, and I'll come on to that in a little while. Also, not all deposits are equal. So using plutonium as an example of a fallout product, if we look at typical activities per gram, okay, so becquerels here, atomic disintegrations per second, for plutonium-239-240, for the 1963-64 fallout maximum, we can see that we actually get much higher activities in sediments. So here we've got an example from Crawford Lake sediment here, 17.8 becquerels per gram detected, compared to corals where we get 0.3 becquerels per gram. And in ice cores, we get much lower activities. So here we get 0.0014 becquerels per gram maximum in the Palmer ice core. Again, these are all candidate GSSP sites being examined by the Anthropocene Working Group. In terms of preservation as well, it's important to think about mobility in geological systems of these radionuclides. So using plutonium as an example, plutonium's typically immobile once it's deposited, but it can, however, migrate in acidic peak profiles. Effectively, that adds anthropogenic plutonium to layers that were deposited before the period of nuclear weapons testing. Similarly, the carbon-14 present in deep marine sediments, and these obviously represent some of the key materials preserved in the geological record, records a mixed signal of atmospheric and oceanic carbon pools. So there's a mixing process going on there. Iodine-129, which I mentioned earlier, also is reasonably mobile in sediments, but certainly under redox gradients can be mobilized. But it's important to point out that the signal is effectively global and can be detected using standard counting techniques in sediment, soil, coral and ice. So even with the very low activities present in ice, example here from Liz Thomas et al., the Palmer Ice Course, part of the Anthropocene Working Group work, shows again detection of plutonium-239-240 by standard alpha spectrometric techniques. These are the standard techniques present in a large number of labs around the world used to measure plutonium and other radionuclides. And it's important to point out as well that there's a very large literature present, already published, in addition to that on the candidate GSSP sites. So particularly since the 1960s, there have been a huge number of studies on looking at the signature of radioactive fallout products in ice, coral, sediment and soil. An example here just for plutonium, showing a range of different sorry, I know it's very small, but a range of different publications covering ice cores, corals, estuaries, marine sediments, lake sediments, etc. So there's a very long literature looking at these fallout signals and discriminating these fallout signals within geological deposits. It's not just the work that's been done by the Anthropocene Working Group. Just to move on finally really to the idea of source fingerprinting. One of the things we can do with plutonium is we can actually look at isotopic ratios to determine the source of that plutonium. The example I've given here is a profile of plutonium 240 to 239 isotopic ratio in a salt marsh deposit near to the Sellafield nuclear facility in the UK. And it's quite an interesting profile because in its early phases, Sellafield was primarily producing plutonium for nuclear weapons manufacture. And we can see that in the lower part of the graph. For nuclear weapons manufacture, generally the amount or the ratio of plutonium-240 is much lower. So here we have much more plutonium-239. That's the fissile isotope, and that's the preferred isotope for use in nuclear weapons. But over time, Sellafield moved on to the reprocessing of spent nuclear fuel rather than plutonium production for nuclear weapons. And so we can see that very clearly in this profile. At the base, we've got very low plutonium-240 to 239 ratios, which increase to a value of greater than 0.2. The reason for that is that the plutonium isotopic ratio depends on for a nuclear weapons test, depends on the characteristic of the device tested, but also it depends on the burn-up time of the plutonium. So here in nuclear reactors, we tend to see a much higher ratio of greater than 0.2 because the plutonium-240 has had longer to be produced. So effectively, the plutonium-240 and heavier plutonium isotopes are produced by neutron adsorption. And so when you've had nuclear fuel being burnt for a prolonged period, a large amounts of those heavier isotopes build up. So the plutonium-240 to 239 ratio increases. So we can effectively use that as a fingerprint for the source of plutonium in the environment. And the table at the top there from Wiertel in 2011 shows the different isotopic fingerprints of global fallout, the Chernobyl accident, the Pacific Proving Grounds, the Nagasaki atomic bomb, fuel hydrogen bomb debris, and the Semipalatinsk nuclear test site. So we've got very different isotopic ratios there that we can potentially use to fingerprint the sources of plutonium in the environment. So moving on now to that source fingerprinting, but also temporal resolution and some examples from the candidate GSSP sites. So apologies for colleagues, again, in case I steal anyone's thunder for the presentations this afternoon. But effectively here we've got an example of Jerome and colleagues' work from the Baltic Sea. And here we can see the americium-241 signature, which can be effectively used as a dating tool in the Baltic Sea sediments. And so we've got a peak there at about 24 centimeter depth, correlating to about 1963. We have a coincident peak in red there in plutonium-239-240. But also, if you look at the isotopic ratios there, plutonium-240 to 239, we get quite high values at the base of the core. And these are actually fingerprints or signals consistent with those from the Pacific Proving Grounds and the early thermonuclear tests. And then we fall to about 0.18, which is a characteristic signal of nuclear weapons testing, nuclear fallout, global nuclear fallout. And then there's a slight increase in ratio towards the top of the core, again shown in this kind of green color, which represents Chernobyl inputs into the Baltic Sea system. So it's potentially a very useful way of fingerprinting the sources of the plutonium, as well as the plutonium activity providing a really quite high resolution marker to an annual level. Of course, we're not just looking at plutonium. There are other isotopic markers, radionuclide markers. So here we can see the plutonium signal in the WFGB coral core, and we've got quite high error bars on there, on the plutonium signal on the left there, due to the low activities we determine. But actually, we've got a really nice signal there for carbon-14, and we see the bomb spike from carbon-14 very clearly in these corals. And there's been quite a lot of published literature correlating those bomb spikes in various corals around the globe, as there has been for plutonium, a recent paper looking at the correlation of plutonium isotopic signals in ice cores and correlating those globally. So I have a way of conclusion. Radionuclides are strong candidates to define an Anthropocene basal boundary. So they are coincident, their appearance and their pulsed input is coincident with effectively the base of the Great Acceleration. They're mostly absent in nature. They have long half-lives that provide a long-lasting signature. So if we consider plutonium-239, that signal will last for greater than 100,000 years, based on its 24,000-year half-life. They have potential to form a relatively fixed and isochronous marker in geological deposits. It's important to note they are commonly used dating tools. So effectively, these fallout products have been used quite widely in the literature as dating tools. They are present in sufficient quantity to be readily detectable. They provide a high-resolution record at a range of GSSP candidate sites covering corals, ice and sediments, and in a wide range of other geological archives in published data from the 1960s onwards. And that records the onset of thermonuclear testing in 1952 and subsequent fallout changes, that pulsed input, with potential for source discrimination to individual groups of tests or input events based on the plutonium isotopic ratios. And importantly, even where activities are very low, advances in accelerator mass spectrometry mean that mass isotopic abundances and isotope ratios can be readily determined. Okay, so the data you've seen for carbon-14 were accelerator mass spectrometry. Some of the presentations this afternoon, I think, will show iodine-129 from accelerator mass spectrometry. For plutonium, we can detect plutonium at sub-femtogram, basically sub 10 to the minus 15 gram per gram concentrations in geological materials. So I think I've been about 20 minutes. I would like to thank you for your attention. And I'd welcome any questions. I'm not sure, Simon, if you're going to do questions now or at the end of mine, Neil and Mark's presentations.
Thank you, Andy. Yeah, we do actually have a discussion period for after this session to raise questions from the three stratigraphic tools we're looking at. So if you could hang on there for a while. We're now going to go to moving away from radiogenic and radionuclides. We're moving to Professor Neil Rose, who is the Professor of Environmental Pollution and Paleolimnology at the Environmental Change Research Centre at University College London. And he is going to be telling us about the, it's down here as combustion products, but I will wager a large amount of money if he doesn't mention SCPs within the first few sentences. He's going to be talking about carbonaceous products, fossil fuel combustion products, I think we should say. Okay, Neil, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, I can. Over to you.
I think you've got my presentation because I can't share from here. Or someone has there.
Yes, we have it here. And I think if you can say next slide when that's required, that'd be great.
Okay.
Thank you.
Yeah. First slide, please.
Yeah, we're just having a problem, Neil, just getting it started.
That's okay, no problem.
Okay, we're good now.
All right, yeah, well, thank you very much, everybody. And echoing Andy's comments, sorry I can't be with you, but I'd like to present today some of the work on the combustion products that we've been doing as part of the GSSP stratigraphies. I'm going to follow a similar format. I want to introduce these markers to you. Apologies if you're familiar with them, and then once I've introduced those to you, then go run through some of the data that we've got from the GSSP candidate sites. So although I'm giving this presentation, it's the work of many others, and I will try and remember to acknowledge those as we go along, mainly Sarah Roberts from University College London, but also Simon, who's been with you, Yongming Han, who's done a lot of the black carbon work, Jun Inoue, who did the work in Beppu Bay, and Stephen Himpson, who did the work in San Francisco. Next slide, please. Okay, so I'm going to talk mainly about particulates today, and Simon's already given the game away about sort of what my main thrust will be, but I want to talk, just introduce this to you. Most of the particulates that we're going to talk about fall along this black carbon continuum. And you can see there is this this spectrum, if you like, of black carbon particulates from charred biomass through across to soot. And this continuum really is from a size distribution of large particles, large biomass particles on the left-hand side, moving across to very small nanometer scale soot on the right. And so you can see in the charred biomass, that image in the bottom left shows showing some sort of structure there. And as we move across the residues of the burning that's going on, we come across to spheroidal carbonaceous particles. There you are, Simon, which is a residue of the industrial fossil fuel combustion, so mainly coal and oil burning. And I'll come on to those in a minute. And they're a sort of micron size. And then finally, and I've just delineated it a little bit by that dotted line there, across to soot. And the reason I've separated them off slightly is because these are combustion condensates. So these are formed within the fuel rather than being a residue of the burning itself. So these are the black residues that come from burning of sort of vehicle fuels, for example. And these are at the sort of nanometer scale. And so as we're moving from left to right in this continuum, we're seeing a temperature increase as we go from sort of lower temperatures to higher temperatures on the right, from small sizes to, from large sizes on the left to small sizes on the right. And therefore, in terms of distribution and transport around the world, we're going from short distances on the left across to much higher distances on the right. Next slide, please. But although I'm talking about particulates in particular, I do just want to mention some of the other combustion products, and I'll come back to them a little bit more later when we talk about some of the GSSP sites. So I could have talked about, obviously there are things like carbon dioxide and nitrous oxides, but also mercury from coal burning, of course, and a range of organic pollutants. And one of the most important ones here, which has been studied as part of the GSSPs, are these polycyclic aromatic hydrocarbons, PAHs. Can you just, next slide, please. And these are divided largely into low molecular weight and high molecular weight compounds. So the low molecular weight ones tend to be like 2 to 3 rings. And the example I've given here is retine. And then the higher molecular weight ones tend to be sort of 5 or 6 rings or greater. And those are the ones I've shown at the bottom, which mainly come from the combustion of coal or from vehicle emissions and so on. And so the low molecular weight tends to be more sort of a natural burning, whereas the high molecular weight ones tend to be sort of from anthropogenic sources. Next slide, please. But the other reason for mentioning PAHs is because they are part of that soot-forming process. So from the PAHs themselves, they go through a series of nucleations, coagulations, and aggregations to form that sort of that soot, or typical sort of amorphous soot structure that I showed you in that previous image. And so there is this very strong relationship between sort of the PAHs and soot and other combustion products as well. So we do expect to see quite a high sort of or range of correlation between these different sources. Next slide, please. So this is the matrix that Colin showed earlier, although as he said, this is a more up-to-date version, so there is a lot more green on here than he showed earlier. So this is one that Simon sent me from June earlier, just a little while ago. And I've highlighted here in bold the ones I'm going to be talking about, so fly ash particles, SCPs, in 10 of the 12 sequences here, but also PAHs, black carbon, and I haven't highlighted mercury, but I could put that in there as well, and that's been analysed in a whole range. So one of the key indicators that we've analysed in the GSSP sequences are the spheroidal carbonaceous particles. I mentioned them a little bit earlier, and I just want to spend a few minutes talking about those in a little bit more detail as we've been analysing them in a lot more, at a whole range of these different sequences. So next slide, please. So these are spheroidal carbonaceous particles, SEM image on the top left there, and some light microscopy images on the right. As I've mentioned, they're only formed by the incomplete combustion of coal series and oil fuels. They have no natural sources, but they also don't have any other anthropogenic sources either. So they are, in that sense, a wonderfully sort of unambiguous indicator of these sources when we find them. They're also morphologically distinct. As you can see, they're very typical. These images are very typical, so they're very morphologically distinct when we see them in our sediment archives. They're composed of elemental carbon, so they're chemically very robust. and so we can use quite strong acids to extract them from different natural archives without any damage at all, and they are well preserved in a whole range of natural archives, as I hope to show you in a little bit. Next slide, please. So why might we think that SCPs would be a good marker for the mid-20th century? Well, again, this diagram on the left here you've seen already today and is very commonly cited. The great acceleration, and the particular marker I've ringed there is primary energy use. Following the Second World War, there was a big increase in primary or demand for energy and electricity, which was met principally by an increased burning of coal and also oil in in power stations for the first time. And so there's this big increase in energy use, and we might expect, therefore, a big increase in these fly ash particles. On the right-hand side here is a modeled information from black carbon emissions from Novikov and others in 2003. And again, this is a global pattern. It's a cumulative figure showing this big increase that we might expect from the middle of the 20th century. And because SCPs are a component of this black carbon, we might expect them similarly then to follow the same patterns. Next slide, please. The other reason for why I think SCPs should be a good marker for the mid-20th century is the scale of the emission from power stations. So next slide, please. If we take a typical 2,000 megawatt coal-fired power station, and I've chosen this because 2,000 megawatts is a fairly typical one. They're quite. It's not a very large power station, but it's also quite. It's not a small one either. So it's a fairly standard one. And typically that would use about 20,000 tons of coal in 24 hours if it's at full operation. And that's 20,000 tons of coal after burning results in about 5,000 tons of ash. A lot of that becomes bottom ash, so it just falls out. And then if we're very generous and we assume that our particle arrestor technology is 99.9% efficient, then that would be about 1 ton of fly ash being emitted to the air. Next slide, please. And if that ash then, because most of the organic content is burned, again, hopefully, and most of the content is the non-burnable material, if we assume that 95% of that ash that's emitted to the atmosphere is inorganic ash, and 5% is SCPs, and then the mass of a 20 micron SCP is about 2 nanograms, then that 1 ton of fly ash emitted to the atmosphere is 25 trillion SCPs, and that's in that 1 day of operation from that one power station. So there's an enormous number of particles being emitted to the atmosphere, which then get transported with the wind and deposited either in dry deposition or through scavenging out of the atmosphere by rain and snow. Next slide, please. So this is so we might expect, therefore, the SCPs to show a very nice comparison with those patterns of emission and energy demand that we've already shown. And this is a compilation of data that I put together in 2015, and quite a while ago now. It seems no time at all since I did this. But there's, and you won't be able to see the detail on this, but essentially this is from over 70 lake sediment records from around the world. And all you need to see here is that red line represents 1950, and you can see that above that, or at that point of that red line, we see very significant increase in the SCP inputs. These are fluxes, so the numbers of fly ash particles per meter or per centimeter per year at that time, or through time rather, and at 1950 we can see that increase is happening. The other thing you'll notice from the figure here is that at that time there was very little data for the southern hemisphere, although now, or since I produced this data, there's more from the tropical or Central America, from Southeast Asia, from South Africa, and also from Australia, and they are now showing very similar patterns. Next slide, please. So in essence then, because we're seeing that very nice signal around the world, we expected to see, or we might expect to see, SCP records showing similar patterns in the GSSP sequencing. And so I just want to spend the rest of my time talking about the records that we've found. I want to start with the Palmer ice core. If I'm honest, I wasn't really expecting to find SCPs in this ice core because of the location. It's a very clean area of the world, of course, and of course the distance to sources. And so I was, I hesitate to say use the word delighted, but we found SCPs in these ice cores. We required the development of new methods for this. We had two different approaches. One was the filtering of melted snow samples, which we then dissolved those filters and then and looked at those in light microscopy in a sort of fairly traditional way that we would have done with lake sediments. And the other one was using this electron microscopy of particulates, which were retained as a byproduct of the, if you like, during the standard ice core meltwater analysis. And so those are the images you can see here. These are a 10 micron particle shown within the lower figure and a 7 micron one just at the top. And you can see the very typical morphologies of these particles there. And so this is taken from Liz Thomas's paper, which has been submitted for that GSSP issue. And you can see that the SCP profiles here are the first record from 1935. We found them and then off and on sort of through the record through to the top of the core, which was 2000. The record here back to 1920 doesn't show the whole picture. My colleague Sarah Roberts analysed these records all the way back to 1900, but didn't find any other particles. So this represents all the particles that we found. We believe that in other parts of the peninsula we may find a more continuous record, but this one, of course, is the sequence that we were analysing. Chemical analysis of the individual fly ash particles themselves revealed that they were of coal origin, so the trace elements on the surfaces, and then trajectory, forward and backward trajectory analysis suggests that these were primarily from South America, not surprising, as this was from the Antarctic Peninsula, and then, or possibly also an Australian source. But more work hopefully coming up on that to try and confirm that information. Next slide, please. The coral cores, again, no one had ever tried to look for SCPs in corals, and again, that required a new method, so we developed a technique for extracting these fly ash particles from coral cores based on some core sequences that were sent to us from Jens Zinker and Diego Kirstang. And we found SCPs in those, or we believe we did. Those are the images you can see here on the right-hand side. Concentration is very low, about 10 particles per gram of coral, and that compares with sort of thousands really in the, even in quite clean sediments, up to 10,000 in some of these sites per gram of sediments. And so these are very low concentrations, but because we can remove pretty much all the coral material, we are able to have a very low detection limit. And all SCPs that we found in these Mediterranean Sea records were after 1950. We didn't find anything before that time. Fortunately or unfortunately, depending on your point of view, we found no SCPs in the GSSP sequences that we analysed, despite analysis of a very large number of annual samples from both Flinders Reef and the West Flower Garden banks in the Caribbean. So we believe that these are then the below analytical detection limit in these regions, although we do intend to try and confirm these other records in the corals. Next slide, please. For the marine sediment cores, we've got 3 here from the Baltic Sea, and you'll hear from Jerome later a little bit more about that one. And Beppu Bay, again, you'll hear about that this afternoon from Mick. And the San Francisco Bay on the right-hand side. I've plotted them together on the same axis, so or same y-axis, so you can see the 1950s plotted across here. The Baltic Sea record there starts in 1950, almost a nice increase just at that time, and peaks in the early 1980s. This is a very typical record that we see in European sediment records in both lakes and now, of course, in marine sequences. Beppu Bay starts a little bit later. There's a continuous record from post-1942 and a rapid increase from about 1962, which, again, you'll hear about this afternoon, is linked to local and regional oil refinery patterns. And then finally, on the right-hand side here, San Francisco Bay. all the SCPs that were detected there. This is by Stephen Hinson's work. Sorry, the Becker Bay there was by Jun Inoue. In San Francisco Bay, all the SCPs detected were post-1960, and it's a very noisy signal, principally due to the high accumulation rate and the low count numbers in that record. Sorry, excuse me. Next slide, please. Just taking one of those records in a little bit more detail, and apologies to Jerome if he's going to talk about this later on, but this is just showing a summary diagram from the Baltic Sea record, and you can see the SCP sort of sitting in the middle there above the image that I put there. That's an SCP from the Baltic Sea from 1992, extracted from that sediment core. And the PAH data, which was undertaken on this core, isn't featured in this diagram, but it similarly shows a peak in about 1981, which is about the same time as the SCPs here. But in particular, the Baltic Sea record shows a very good comparison with Mercury. So next slide, please. And I don't think I've ever seen such a good, we've published a lot of work on comparing SCPs with Mercury because we know they have a very similar source, coal combustion. And I don't think these are both very high resolution records from this sequence. And I don't think I've ever seen such a good match between the SCPs and the Mercury. Here you can see with one or two sort of very minor sort of temporal differences, there's a very good agreement between Mercury and SCPs, again as a linking to the coal combustion source.
Yeah, no problem. No problem. Yes, thank you. Okay, good.
Next slide, please.
Oh, and that's one thing.
Looking at the peat record now, again, you're going to hear from Barbara later on, so I don't want to sort of, again, steal her, what she's talking about. But again, you can see.
Okay, thank you.
Sorry. Oh, okay. Yes, so the SCP record is here in the middle there, and you can see that there's a very good relationship between that and the mercury, but also with mullite, which is an aluminosilicate mineral component of fly ash, the inorganic component that I mentioned earlier. So again, we would expect that to be the case if coal was a principal source. So again, this relationship between mullite and SCPs and mercury is suggesting a very good agreement or an increase in coal combustion as the source of these records here. Next slide, please. So finally then, lake sediment records, and I know you're going to hear from Francine this afternoon about Crawford Lake. So we've got Crawford on the left-hand side here, Searsville, which is a lake above San Francisco in California in the middle, and then Sihai-Long-Wan, which is this lake from China on the right-hand side. And you can see both Crawford Lake and Sihai-Long-Wan show a very nice record from about 1950, this big increase at about that time, again, similar to all those other ones that I showed you earlier from around the world. Searsville, much like the San Francisco Bay record itself, has a very noisy record. And again, this is down to the very high sediment accumulation rate and hence the low count numbers. As Andy mentioned in his talk, not all sequences are created equal, and so we're not seeing that very nice signal that we're seeing in the others at this particular site. Although the record is sort of the first presence of SCPs occurs sort of from about the 1930s there. Next slide, please. But just to take one of those sites again and compare it with some of the records, this is the sediment record from Sihai-Long-Wan, and so we've got the SCP profile on the left-hand side here, and then the PAH data, and then the soot on the far right. And you can see that there's a very good relationship, as I mentioned earlier, as you might expect, between the PAH records and the SCPs, in particular the high molecular weight PAHs, again, as you would expect, because those are produced from the industrial signals. And so we can see that there's we're seeing this very good record increasing from about 1950. Slight differences between the SCPs and the soot, again, because these are from slightly different sources. A lot of the soot will be coming from vehicle emissions, for example. So we wouldn't necessarily expect to see a very good relationship between the two. but in general, the patterns are similar. Next slide, please. And this diagram is taken from Yongming's paper, which has been submitted as part of the GSSP papers, and this is a correlation matrix just showing the relationship between SCP concentrations and accumulation rates with the other measured parameters. And you can see the red ones are where there's a positive correlation, and there's a very high agreement there between SCPs and a large number of the other sort of combustion products, so soot and mercury and those PAHs that I've already mentioned. Next slide, please. So to conclude then, the combustion products, they are directly related to a major driver of the global environmental change, fossil fuel combustion, and they're preserved in a broad range of natural archives. The GSSP sequences have been produced here are some of the most high resolution ones that I've ever seen. So particularly from the peats and marine sediments, they're the highest resolution, and probably also from the lake sediments. The ice and the corals, again, required new methods, and these are the first record for SCPs in the ice, or Antarctic ice, and we were surprised, as I said earlier, to find them there, but to see the record that they have from the middle of the 20th century onwards, or from just before the mid-20th century. So a number of these sequences are showing significant increases in SCP concentration starting from the mid-20th century, and many of those are showing very good correlations with other combustion products, such as the soot and the PAHs and mercury, but also with other potential markers for the Anthropocene, such as plutonium PCBs, these polychlorinated biphenyls, and DDT and other markers, microplastics and so on. So they form this very good array of markers present within the sediments to define the Anthropocene from the mid-20th century. So with that, I'm finished. Thank you.
Thank you, Neil. So again, we'll take questions after our final speaker on SCPs, and I'm very pleased to introduce Professor Mark Williams, who is a professor of paleobiology at the University of Leicester in the UK. So you can't be here today, Mark. I think you'd like it in the natural history section. So if you'd like to start now, and again, we'll take questions for all the speakers after this presentation. Thank you.
Thank you, Simon. Hopefully you can see my screen and you can see my presentation. If you could just confirm that.
Yeah, I can see a lot of it.
That's great. Thank you, Simon. Yeah, I'm really sorry also not to be able to be in Florence. I'd love to be there with you, but I am delighted to be in this group of three with Andy and Neil, and hopefully I can build a little bit on what Andy and Neil have already presented. So we wanted to begin with this image. So this is very much a collective effort from myself, Stephen Himpson, but many colleagues within and without the AWG. And we thought this image was really telling because it shows a snapshot of marine traffic on planet Earth at any time, and equally we could have shown air traffic or road or rail. And what it's showing is that the world is interconnected in a way that it's really never been in 4 billion years of biological evolution on this planet. And the results of this interchange and of the human technology that drives it is really a wholly reconfigured biosphere, which is leaving a paleontological signal that's very clear in the fossil record. So I want to begin by actually asking the question, how have humans modified the biosphere, and then looking for some of the paleontological signals that are associated with that. And the figures really are quite staggering when you start to look at this. You and I, as a species, Homo sapiens, are more than 99.9% of the numerical abundance of all primates on this planet, staggering for a single species to be so dominant within a group. You and I and our domesticated animals are 96% of the terrestrial mammal biomass. Again, that's a staggering figure for one species to dominate the terrestrial realm and its animal biomass in this way. We have radically modified the organisms that exist in those ecosystems that we've changed. So if you look at one of the things that we really like eating, the chicken, the modern broiler chicken is far removed from the ancestral ecology of the red jungle fowl that occupies the jungles of Southeast Asia. And this is what we've done to chickens in the past 70 years because we like eating them. We eat 63 billion of them every year, and we have substantially changed their biomass and anatomy as a result of this. We have modified half of the habitable land surface for farming. Again, a staggering figure for a single species to do. And of course, we've also heavily modified the oceans. 3/4 of the land that is farmed is for animals and dairy, and about 1/3 of the land under crops is also used to feed our farm animals. So again, staggering figures for a single species to dominate the Earth system in this way. Crops like maize, wheat, and rice are now produced in vast quantities, over 2,000 million tons per year, and are consumed, of course, globally. We have relocated species on a colossal level across this planet. This is a process which has certainly been unfolding for thousands of years, possibly tens of thousands of years, but it has accelerated, particularly in the latter part of the 20th century. And some recent very good studies by Hanno Siebens and colleagues at the Settembre in Frankfurt have quantified this from tens of thousands of records. A very rapid rise in the past couple of centuries, but an inflection and even steeper rise in translocation of species in the mid and later part of the 20th century. Now, all of those changes to the biosphere have put many species at risk of extinction, and indeed many species have already gone extinct. Colin already alluded to this in the first presentation this morning. Of course, the true figure may be much greater than we know because we haven't even quantified the degree of biodiversity in the biosphere at present. We're nowhere near quantifying it. So processes that have driven these changes to the biosphere include hunting and gathering, landscape domestication, and globalization. And of course, these processes, as Colin alluded to, have unfolded over a very long period of time. We want to ask the question, do any of these leave a fossil record that can characterize the Anthropocene? Of course, what we're looking for are fossil signatures that are readily discernible, that can identify discrete and successive geological intervals. We want organisms, fossils that are abundant and geographically widespread, will occur in a range of environmental settings that would permit global correlation. And of course, what we're looking for are first appearances that will effectively define an isochronous surface between multiple regions of planet Earth. Well, what we're going to demonstrate to you is that at least one of those signals that we've highlighted at the start here can be used to characterize deposits of the Anthropocene, and indeed is part of this profound signal of change to the biosphere. Let's just go through all of these different processes in turn. I want to begin with hunting and gathering. Of course, hunting and gathering is a component of the species Homo sapiens, but also of the ancestral species in our genus Homo. So this goes back millions of years. But we can see clear evidence, of course, of the impacts of humans on the planet, again, as Colin alluded to in his opening presentation this morning, certainly from around about 50,000 years ago with the megafauna extinctions. Now, megafauna extinctions have left a very distinctive paleontological signal, and that paleontological signal is worldwide. But it's very evident that that signal is uneven in terms of its chronological expression and also its spatial expression. So the impacts of humans on the megafauna in tandem with environmental changes like climate change are certainly greater in those regions of planet Earth where Homo sapiens were the first human species in the landscape. So might we use this to characterize the Anthropocene? Well, despite the detailed extinction chronology available for several species, the temporal data are unavailable for many extinctions. Associated palynological signals in some cases provide regional biostratigraphical markers, but they don't provide a web of correlation that can be applied worldwide. And also, this is time transgressive over 50,000 years. It's still continuing at present, and it does not fulfill the criterion of synchronicity that's needed to characterize a chronostratigraphic boundary. What about landscape domestication then? Again, we could say that this started to begin about 13,000 years ago, but it's part of an episode of change over a very long interval of time. Indeed, some people have suggested that humans were trying to experiment with cultivating wild cereals as long ago as 23,000 years ago. So landscape domestication leaves a very distinctive paleontological signal, and that's worldwide. But the problem here again is that this is very diachronous in terms of its expression. So these developments were strongly asynchronous, development of landscape modification at the regional and intercontinental scale, and indeed was subject to reversals resulting from climate and environmental change. And no one group of fossils here, including translocated crops and domesticated animals, provides sufficient fidelity to develop an interconnected web of correlation that can identify an isochronous boundary globally. And this counters the suggestion that the Anthropocene in effect equates to the Holocene, again, something that Colin alluded to in his opening presentation. What about globalization? Does this express as a paleontological signal that we could use to define the Anthropocene? So we're taking a date here of around 1500 CE, the start of the Columbian Exchange. But of course, globalization is also part of a process that's unfolded over a very long interval of time. There was interchange across the Indian Ocean long before 1500 CE, and also the developments of interchange at an intercontinental level, for example, through the Silk Road. So globalization from the Columbian Exchange resulted in the exchange of many organisms that we're very familiar with. This is a figure that Colin drafted a few years back, showing the redistribution of maize around planet Earth after the Columbian Exchange. And this has left a fossil signal. So you can find pollen of maize in African lakes from the early part of the 18th century. Or, for example, we might be able to find the pollen of tobacco in a 17th century clay pipe from Rembrandt's house in Amsterdam, found there in the cesspit. So clearly there's a global signal of this, there's a global paleontological signal of this. The problem is that none of these early Columbian Exchange signals are widely documented from the sedimentary record, and none of them provide an isochronous set of markers that we can use to define an Anthropocene series or epoch. So what about the later stages of globalization? We started with this figure, which expressed the way in which humans move products around planet Earth, and part of that means an interchange of organisms as well. What we found as a group, working collectively to try and pool our knowledge, is that by the 20th century, it is possible to define intervals of time in the sedimentary record based on the translocation of non-native species and their fossil record, which can define very well-defined intervals of time in that century. We're showing here 3 potential intervals that could be defined in the early part of the 20th century, the mid part of the 20th century, which would be a really good marker, obviously, of the proposed boundary for the Anthropocene, but also in the later part of the 20th century also. And of course, that dovetails with some of the profound changes that have already been discussed in detail by Andy and Neil. And we wanted to show you a working example of how biostratigraphy and paleontology can really provide very high resolution determination of Anthropocene deposits, and also an ability to correlate those deposits both within a basin and beyond that basin. So we're going to show you the example of San Francisco Bay here, which has been very much the work of Stephen Himpson, a PhD student at Leicester. Stephen got his PhD last week, so is now Dr. Himpson. So this is also San Francisco Bay, one of the places on planet Earth where introduced species have been documented with very high resolution. And this is very much the work of Cohen and Carlton and others like Mary McGann at the United States Geological Survey. And what we find also in San Francisco Bay is that there's this inflection in the mid to late part of the 20th century with an increasing number of introduced species recognized in that interval. The Manila clam, for example, arrives in the middle part of the 20th century. And it's an invasive species. It obviously comes from the Western Pacific, from the area of the Philippines. And many of these organisms, when they find their way into San Francisco Bay, proliferate and spread through the bay very, very rapidly. So here you can see Manila clams in San Francisco Bay. There can be as many as 2,000 individuals per meter square, basically obliterating space for the indigenous organisms. That's the Manila clam. We can show you a whole series of these. This is the Amur River clam, also in San Francisco Bay, and obviously this has come from East Asia also. It arrived in San Francisco Bay in 1986, and then it proliferated, and you can see the way this species has proliferated. Now, in some regions of the bay, we can find nearly 20,000 individuals of Amur River clams per square meter, and they have literally obliterated space for the indigenous organisms to thrive in and change the ecosystem there. Now, you might expect, if we're getting these kind of organisms that are shell-bearing, invading San Francisco Bay, that they would leave a fossil record in the sedimentary record of San Francisco Bay of Anthropocene deposits. And that's exactly what we've tried to do. So we first of all devised a theoretical biostratigraphy of species we thought we might find in the sedimentary record of San Francisco Bay because they have recalcitrant skeletons, so things like foraminifera, gastropods, mollusks, etc. So this was a theoretical basis, and then we've gone away and we've tried to actually ground truth this in the geological record, or Stephen has very much done this work. So we went out into San Francisco Bay, we made a whole series of new cores in collaboration with the United States Geological Survey, and particularly with Mary McGann there, and we also built on the existing record of cores from San Francisco Bay. What Stephen was able to do is recognize that some of these non-native species do form widespread markers in many of these cores from San Francisco Bay. And these include organisms like ostracods that you can see top left there, foraminifera that you can see bottom left there, and mollusks that you can see on the right there. So this is the very detailed biostratigraphy that Stephen produced of one of those cores, core San Francisco Bay 20A. You can see that we've got some markers in this core for different chronological markers. So the one down there at bottom left, early mid-60s, is the mercury spike that we find in San Francisco Bay. And the one up there we're showing at 2000 is a eutrophication event, which is widely recorded across the bay. And then what Stephen's done is actually plot the stratigraphical incomings of the different introduced species. So we've got invasive ostracods from East Asia in the middle 1970s. We've got the invasive foraminifera, Trocomina haydai, appearing in 1983. And we've got the invasive Amur River clam appearing in 1986. And the importance here, and I hope you can all see this, is that these species are coming in order in the sedimentary cores of their observational record of them actually finding their way into San Francisco Bay. Now here we're showing you the signal from a single core, and we're showing you that biostratigraphical characterization of sedimentary deposits in San Francisco Bay is very plausible, and it works, and we get the order of biostratigraphical succession that we'd expect from the chronology of invasion. But Stephen then took this a stage further. He used ranking and scaling software to actually examine whether it was possible from the whole record of biostratigraphy in San Francisco Bay to correlate across the bay. And he's been able to do that with very high resolution across some 20 cores covering the whole of the Bay Area. And he's been able to subdivide this into 7 zones based on a whole range of different biostratigraphical and non-biostratigraphical criteria. And you can see that this works very well. It works as a biozonation, just as we try to build a biozonation in the Silurian or the Pliocene or wherever in the geological record. And this, of course, is a very high resolution biostratigraphy for Anthropocene deposits in San Francisco Bay. Now that's San Francisco Bay, and we've demonstrated that within that basin we can characterize Anthropocene deposits from the fossil record of invasive species, and we can correlate across the whole bay. What about trying to correlate between regions that are widely apart? What about trying to correlate 4,000 kilometers across the Pacific Ocean? Well, of course, San Francisco Bay is not the only invaded ecology on planet Earth. Many ecologies are very highly invaded. The Hawaiian Islands are one of those ecologies where, again, the record of introduced species has been examined in very high detail. So we could look, for example, at the record of invading snails, and they very much are invasive species on the island of Kauai during the 20th century. The giant African snail is introduced, and the cannibal snail is introduced. And you can probably imagine what happened to the indigenous snail faunas as a result of these changes to the ecologies. And those changes are recorded in the stratigraphical record of Kauai. So, for example, you can see here very clearly that in deposits of the later part of the 20th century, the fossil record of gastropods is that of invasive species, whereas the record in older sedimentary deposits is very much that of the indigenous species, which have now been extirpated on this island. So here again, a very, very clear paleontological signal of deposits of the mid to late 20th century. Well, those are just a selection, and these two are just a selection of the potential biostratigraphical markers that we think we will be able to use to define deposits of Anthropocene age globally. So can this be used to characterize the Anthropocene, or Anthropocene deposits, as defined, if defined, for the middle part of the 20th century, for the boundary? Yes, we believe a web of correlation can be built to characterize sedimentary deposits of the 20th century, just as we would do in deep geological time. And of course, this dovetails with other primary signals of the Anthropocene. How does this compare with other epoch series boundaries in deep time in terms of the paleontological characterization of them? So here we're showing you the Anthropocene on the left-hand side, and on there we've also plotted all of the kind of human impacts on planet Earth, both of Homo sapiens and of our ancestral Homo species also. And there at the top sits our global web of introduced species in the mid-20th century, forming a really good biostratigraphical marker of that interval globally, and bracketing, providing a bracket on which we can also contextualize all of that deep time change to the biosphere that humans have clearly induced. And that compares very well, for example, with the biostratigraphical definition of the Wenlock-Ludlow boundary in the Silurian. It's defined on the basis of a graptolite species, assumed to be isochronous in its occurrence around planet Earth. And that also brackets an interval of major biological change on planet Earth that underwent change over about a 2 million year period before that boundary. Or we could look at the Upper Ordovician, Clandovery series boundary. It's also the system boundary between the Ordovician and the Silurian systems. Again, it's bracketed by a graptolite species, but it also forms a means of contextualizing a substantial interval of biological change that happened before that boundary. So the strong similarity here in the way in which we might paleontologically characterize the Anthropocene compared to other geological boundaries in deep time. A final conclusion then. I think we've demonstrated as a group very clearly that paleontology has a significant role to play in characterizing deposits of a 20th century Anthropocene. But I also think, and it kind of refers back to some of the conversation between Colin and Emmeline Costa earlier on in the conversations today, that also this paleontological signal is a primary way of humans actually demarcating in the geological record the very significant changes to the biosphere that have occurred and which are accelerating as we go into the 20th and 21st century. Thank you very much.
So thank you, Mark, and thank you to the other two speakers. I think we'll take questions now. There's an awful lot of material there to go through, from radionuclides to carbonaceous materials and modern paleontology. But if any questions here in the room you have, could we have them now? And then we'll go to the online audience. Any questions? There's a question there. I think there's a microphone you'd like to use.
To work? Yes, it does. I would like to ask to Mark a question about, paleontology and, diversity dynamics in the San Francisco Bay. So he showed very well, history of invasive species. So my curiosity essentially is at local or regional scale. So the San Francisco Bay, do they see any decrease in diversity? So those invasive species cause a decrease in diversity. So is there any documented extirpation or extinction, or simply there is a shift in dominance? So in certain part, you get invasive species. In other part, you get, autochthonous native species. Thanks.
Did you hear that question, Mark?
Yes, I did. Thank you, Simon. I mean, it's a great question. It's a really good question. I mean, the specific case of San Francisco Bay is that is essentially a substantially human-modified ecosystem now. So, and this is very much the work of Cohen and Carlton, Mary McGann, and then Stephen, quantifying that. In some parts of the bay, 97% of the biomass is introduced. So it's obviously had a very, very substantial impact on the overall ecosystem. What it hasn't done yet is produce an extinction event in the local organisms. So they are managing to survive in places, and the ecosystem in that sense is not less biodiverse. And of course, that's part of the mosaic and tapestry of change that's very evident on planet Earth, that the interaction of ecosystems with introduced species is very, very complex. Sometimes those organisms are benign, sometimes they're beneficial indeed, but also they can be very detrimental to those ecosystems. And I use the case of Hawaii because one of the places that we've seen extinction really play out very, very substantially on this planet is in island ecosystems. It's very, very substantial paleontological signal now, not just on Hawaii, but you go to Madeiran Islands, you know, any kind of island ecosystem on the planet. And, you know, the point, one of the reasons why we're trying to do this is because we are now trying to make direct comparisons between the deep time geological record and the present fossil record. And really you can only do that if you actually try to quantify the changes in places like San Francisco Bay. I hope that answers the question. It was a bit long and convoluted, sorry.
That's okay, thank you.
Are there any more questions here? And are there any more questions on the online? Has anyone raised their hand? There's physical hands being raised in Florence. It's very exciting.
Hi, my name is Silvia Danise. I'm a paleontologist, so I work on ancient, on Pliocene or like Jurassic sediments. So my question to Mark Williams is why he decided to use the work fossil and paleontology for remains that are so recent. I understand that they are like dead shells, but I would like to know why he uses the term paleontology for them.
I mean, I think processes of fossilization begin the minute an organism dies. That's certainly basically what the science of taphonomy is. So I think from that perspective, the fact that these are you know, organisms that are preserved in the very recent record, I see no reason why we can't refer to them as paleontological entities. You know, that they're the shells of organisms, the skeletons of organisms that are preserved in the sedimentary record. So therefore, I don't see any problem with the definition of you know, of a fossil being very recent. And I mean, there are other studies. You know, there's the recent Plotnik paper that, for example, looked at the distribution of you know, humans in graveyards, for example, and you know, and is also considering them in this kind of context. So I think it's a definition of paleontology which is predicated very much on taphonomy. Does that hopefully answer the question?
Yes, I mean, it does. I think we could discuss a lot about it. I mean...
I agree.
Thanks.
There's another question.
Hello, Mark. Thank you very much indeed. Sorry, Martin Head, Brock University. Thank you very much, Mark, for that very interesting talk. I'm just wondering, it in fact just occurred to me that perhaps taphonomy and bioturbation could also have an impact on the actual stratigraphic positions of some of these fossils. Does that create problems for you at all in your core?
So, yeah, I mean, obviously that's a very, very strong consideration. And it's something that we looked at in a lot of detail. I mean, as of all of these studies, of course, they've all had a very strong multi-proxy approach. And we certainly don't have the kind of annual resolution, you know, from the sedimentary record that, for example, many of the other GSSP studies do. But what we have done is a very, very detailed taphonomic analysis of the paleontology of the fossils that Stephen's done it, of the fossils that we found in the San Francisco Bay core. So, for example, Stephen was very careful to look at the size distribution of his ostracod assemblages and to compare them to kind of statistical evaluations of biocenosis versus thanatonosis for ostracod assemblages that have been well documented. So we've certainly tried from a taphonomic perspective to avoid any problems of major biodegradation or disruption of the core. And we actually don't have any very clear physical evidence that there is strong biodegradation in the core. And I think one of the key clear demonstrations of that, Martin, is that in that very narrow interval where Trochamina haydai arrives in 1983 and then proliferates, they proliferate incredibly fast, these species, and where the Amur River clam arrives in 1986, Stephen's been able to replicate that order of succession in a whole series of cores across the bay, which suggests that the biostratigraphical resolution is very high in these cores and can pin them down to a couple of years, really.
Thank you very much, Mark. That's very interesting.
Hello, I'm Stefano Dominici. I'm a paleontologist working here in Florence at the Natural History Museum. Of course, my question is about the last talk, and I question the fact that we are talking about species that either are terrestrial or shallow water and that have a limited geographic extent. So the comparison with the graptolites, which were pelagic organisms and that were chosen in the Ordovician as markers, is that because they were widespread across continents. So we are talking about two classes of organisms that are really not much comparable. Second thing that I'm going to ask you is about the choice to work on an epoch and not on an event. And my criticism comes from the fact that we have a limited stratigraphic record of this quite recent event, 70 years ago, that is going to change because with the transgression we will have an increased hiatus and bioturbation will reasonably mix. So we will have extended time averaging of benthic community of the shell benthos of the remains of these organisms in the future hundreds of years because of the transgressive sea level. So we are always very we advocate caution in comparing the present case, the Anthropocene event, with geological events. And also there is a cultural, I'm perplexed from the cultural point of view because we have the quaternary that was historically established to advocate that we have an epoch that's tied to the advent of human beings. And then we have the Holocene that is also connected with something that is tied to humans and to human cultures. But epochs traditionally are very long units from the time scale and particularly from the stratigraphic scale that would allow us to recognize them through continents. And here we are talking about a very thin object, a very limited object that is perplexing me. This also on historical, cultural grounds. Of course, my question is too complex to be answered by Mark alone, so I would like to limit my question to the first part. Thanks.
Again, that's a great question and really valuable to make a comparison. I mean, you talked about graptolites being plankton so widely distributed through the oceans by natural processes, by ocean currents, for example. But I would argue that non-plankton have now been spread by humans as the vector in a similar manner. So, you know, there are many species there that we showed, the giant African snail, for example, the foraminifera Trocomina haydai, that have actually got a very, very wide geographical spread around this planet in a relatively short space of time, and they are clear markers, in many cases, of the Anthropocene. So, and that is unique. That is unique to humans. No other species could have translocated organisms in that way in 4 billion years of biological evolution on this planet. So I would say that the paleontological signal, it's a web of correlation. We can build one as good as any paleontological definition of any geological boundary in deep time. So that's the kind of question I would say to that. Answer, I would come back to that. Question two, an increased hiatus will be associated with the stratigraphic record. Well, I mean, I think, again, that comes back to some of the comments that were perhaps made to Colin also earlier, you know, about what will happen in the future, whereas, of course, we're examining the sedimentary record as it exists at present as geologists. That's what we do. We can't kind of, you know, speculate on what the geological record will be 200 or 300 years even into the future. And, of course, you could also level that argument at any stratigraphical interval in that, you know, eventually the rock cycle will claim everything. But I also think that many of the basins that we've chosen to examine, you know, there could be marine basins too where you'll find signals. There's likely to be a strong paleontological signal preserved in those settings over a very, very long period of time. And that paleontological signal is vast because the changes to the biosphere are profound on this planet. So I think, you know, both, they're very, very good comments, but I think both can be addressed by what we're trying to do. And if I can say one more thing, and I feel really sorry because I feel like I've been hogging this, but you know, the primary marker that I voted for is actually the radiogenic spike, because I think it's an absolutely wonderful marker. But I think that paleontology also has a role to play in helping to define Anthropocene deposits.
Thank you.
Yeah, are there any more questions on radionuclides and carbonaceous materials? I think one of the beauties of paleontology and the other two is like how the evidence from one of those themes does not contradict the evidence from the others, and that's what we're seeing from a lot of this multi-proxy material. But it's this, like Mark calls it, a web of correlation. It's not just in paleontology; it's in all the multiple proxies we're analyzing. So radionuclides show a very distinct signal, as does carbonaceous particles, but you can also see it in the paleontological record. So it's not just fossils and it's not just radionuclides, it's this combination of material. And we'll later, some of the posters, I might as well highlight the posters we're going to be talking about later. We will see some of this multiple proxy evidence being displayed, and we'll also come across it later when the GSSP candidate PIs present their work. Are there any more people online who might want to ask a question? Okay, Jan, can you hear us?
Yes, I can. Thank you. Yes, that was a fascinating set of talks and questions and discussion afterwards. And I do indeed have a question about the SCPs. I learned lots of new things this morning, including possibly unlearn something. In that, Neil, you said that SCPs had no natural analogues. And here and there, I've read that at the KT boundary, there are similar particles, again produced by high temperatures, by impact, and that are some kind of analogous marker for an event like this. Was that just an urban legend, or are these end Cretaceous particles significantly different, or are there other potential near analogues? of industrial SCPs.
It isn't an urban legend, but they are quite clearly distinguishable from SCPs produced from industrial combustion. The one at the boundary you mentioned was, I think, where the impact was into some high organic matter sort of deposits, if I remember the paper correctly. But the particles that they found actually were almost like SCPs that hadn't been burned. So they showed the inflation of where SCPs are formed by, sorry to go into too much detail, but SCPs are produced by these particles being put into a furnace. Particularly the oil-fired ones, sort of expand, and then the combustion starts in the gases that are emitted from those particles, and then the burning comes back to the particle later on. So the particles that are actually seen in that sort of boundary collision, and there's also another example I've seen from some of the Bronze Age, from some furnaces that have been produced. They've actually produced almost like small particles which have gone through that inflation process, but then haven't burned. So they are you sort of like see SCPs, but with like a skin over the top. But they're not SCPs at all. They're easily distinguishable from them because they're not even black. Actually, they're very easy to see they're brown, and as I say, they haven't gone through that combustion process. So in that sense, they are quite distinguishable from the particles that we know and love from the sequences that we've been looking at.
Okay, many thanks. It's nice to have that cleared up. Just if I can tread on your patience just a little longer. Again, something new I learned was that 95% of the particles coming out of the power station are the inorganic ash spheres.
Yes.
Which I know have been worked on by Frank Oldfield and others. In your opinion, how do those compare in utility? For recognizing, the kind of stratigraphy and recognize the Anthropocene in the way that we're doing?
Well, they would compare very nicely. And as you'll see from Barbara's work, or the work that's been done on the Snieżka peat land, the inorganic particles, the mullite shows a very good relationship, as you would expect, with the SCPs in that sequence, and that's mainly because the coal is the main source there. Funnily enough, when we first started discussing this project, Colin and I had a discussion about whether we would include the inorganic ash spheres as well, but it takes it's much more long-winded way to extract them from lake sediments because they're not, as I mentioned in my talk, they're not chemically very robust. So when you go through the extraction procedure, you have to use a much gentler procedure in order to extract them from sediments. So you get this they're aluminosilicate, so we can't use a lot of the acids that we would use to extract the SCPs, which are robust, which are sort of resistant to those. So you end up with a lot more material. It takes a lot longer to do that analysis, and to do so on these high-resolution sequences. Then we find it would have taken a lot longer to do that. To do that work. The other thing about the inorganic ash spheres is that they are, at least morphologically and to a certain extent chemically, very similar to some natural particles. So microspherules from volcanoes. There was some work done in the 70s or 80s by Roger Lefebvre, who had a fishing line which he had put over Etna and sort of found some very small spheres there. And also, of course, micrometeorites have a very similar pattern as well. And in some lights, if you don't look at them very closely, then of course chrysophyte cysts also have a very similar morphology in sort of sequences. So there are a lot of other, and of course you can't extract those chemically because they're made of the same sort of material, so we can't separate those chemically. So it's actually much more difficult to separate the anthropogenic from the natural inorganic ash, which is why the SCPs are a preferred signal in this sense.
Okay, many thanks. That's most illuminating. There really is a whole world in a grain of ash.
Thanks, Jan.
We just have should we just take one more question here from Barbara?
No, it's not a question. It's just a comment to Neil Rose. I regret that my colleague Beata Smiakrol is not here because I asked her how to distinguish CAP, spheroidal aluminosilicates, from natural particles, and she said that it's possible, and we have material, for example, from Iceland, and she's able to distinguish perfectly anthropogenic particles from natural ones. So I think that depends on specialists, and it's possible to distinguish natural one from anthropogenic. Yes, that's all. Thank you.
Okay, thank you, Barbara. I'll be interested to see how you do that.
Oh yeah, we have a question from Yoshi. Yoshi, would you like to ask it, or shall I read it out?
Would you show you?
Yeah, we can hear you, Yoshi.
Okay, so my question is, thank you, so Andy, so nice review on the radionuclides. So the big bomb test was occurred in November 1st, 1952. That means the 1952 year sediments, just only the 2 months after the bomb test. So the as a base of the Anthropocene, 1952 sediments, it's a good marker or not? So maybe there is a time gap between the bomb test and the sedimentary record. So that is my questions.
Thanks, Yoshik. That's a really good question, actually. There is a slight lag. It depends very much on atmospheric circulation patterns, and also the height of material injection, radioactive material injection into the stratosphere. But effectively, looking at the timing of nuclear tests and the deposition of fission products, a lot of work was done in the 60s on strontium-90 due to concerns of it building up in human populations. And the time lag is anywhere between 3 months and 18 months normally. So there is a lag between injection into the atmosphere and deposition in the sedimentary record. So it's really kind of 52, 53. I think what I would say as well, though, is we need to consider the incorporation of that plutonium into the record and what happens once it's in the record. Because when you're picking up the first point, the first inflection point, you have to be very careful, particularly in sediments, of downward migration through. We've mentioned biotubation earlier, a slight downward migration. So it can be quite difficult to pick up that inflection point. So I think I'm generally more comfortable with saying, it's 52, 53 or early 1950s than actually saying, yes, it's the 1st of November 1952 is when we see this in the record. There will be a slight delay.
Yeah, thank you very much.
Do you want me to say something as
well? I was just wondering, Jan, have you got another question, or have you just forgotten to take your hand down?
Sorry, my hopelessness with computers, I shall lower my hand.
Can I just raise a point then? Yeah. Just further to Yoshi's question, I suppose if we had a look at the analogue of the KT boundary, where the impact expression had a degree of diachroneity, and the solution they came up with was to actually recognise the impact event itself as the start of the Cenozoic. And I suppose you could argue the same could happen then if we decided that the plutonium signal is the key signal, our primary marker, that you use that first expression of the signal, and so that would be, to a large extent, the global signal, and the one that can be recognised by looking at plutonium isotope relationships is 1952, and that we recognise that's the first significant change related to the Ivy Mike detonation. So it becomes a sort of a quasi GSSA. It's a date, but linked to something that has a physical expression in the stratigraphy.
Hello, Yoshi. This is Martin Head here. Good to have you with us. A good question, an interesting question as well. And I think relevant to your question is the boundary, for example, between the early and the middle Pleistocene. The base of the Chobanian stage, for example, is defined at the base of an ash layer, the Byakubi, or the Ontaki Byakubi E ash layer. Now that ash layer is 1.1 meters below the directional midpoint of the Matuyama-Brunez boundary, as you know. And it is the Matuyama-Brunez boundary which is used for global correlation. So that is the primary guide. But the primary guide is not exactly where the GSSP is. The GSSP is at a marker that allows recognition of that GSSP locally, and in the case of the Chiba section, regionally, but not globally. And I suppose it would be the same, well, it's the same with any GSSP, and it would be the same with the Anthropocene as well. Whichever candidate site is chosen, there would be a local/regional marker that would be used for local and regional recognition of the precise level of that GSSP, and then there would be a primary marker which would be close to, but not necessarily exactly at, the GSSP itself.
Yeah, thank you, Martin.
Okay, well then, I think we should probably call that session to a close. Okay, quite complicated. There's a visit after lunch, but I think right now we should stop for lunch and take full advantage of being in Florence for lunch. And then we start again at 2:30.
But online,
so
3:30.
But online, it's 3:30.
Okay.
So thank you to all people listening online and also people here. Thank you.
Yeah. Can you see?
Yeah, that's good.
Okay. So you can also hear me, yeah?
Yeah, very well.
Good. Yeah, fine. Okay, so good afternoon. Yeah, it's nice to be here, even if I'm not completely here. And it's a pleasure, of course, for me and Julia as well to present the data from the East Scotland Basin as a candidate for the Anthropocene series GSSP site. And as you can see here, so me and Juliana, as Colin said, we are working at the Leibniz Institute for Baltic Sea Research Environment in Germany. And there are a lot of people who have been involved also in this study. I'm not going to go through the whole list, but of course we are very thankful for their contributions. Okay, so just here to put the Baltic Sea back together with the other GSSP site. So the Baltic Sea is located here. I will put here, and you see there is a connection with the North Sea. Okay, so there's a relatively big anthropic pressure on the Baltic Sea because there are about 85 million people living in the catchment area. And as you can see here from the these red dots, they are mainly in the southern and southeastern part of the catchment area. There are also a lot of river input, a lot of rivers in the catchment area of the Baltic Sea, especially in the northern part of the Baltic Sea. So it's like more than 200 rivers. And if you look at the sea surface salinity, because of this freshwater input, there's a strong gradient. It's below 2 here, and then when you go towards the connection with the North Sea, you reach salinity around 25, 30. And there is also a salinity gradient at depth, as you can see here on the bottom, because actually of the intrusions of salty North Sea water to the central Baltic Sea. So if you look again at a vertical salinity gradient, profile here from the North Sea and then going through the central Baltic Sea with these deep basins. This one actually is the East Scotland Basin, and then to the north. So you see here this profile, and you see that in the central Baltic Sea you have a strong salinity gradient, which is actually isolating the deep water from the surface water. So it's just like a lid. And because of this, but also because of the input of nutrients, so especially nitrogen and phosphorus, since 1950. So this is because of the beginning of intensive agriculture and using of artificial fertilizers. This triggered the eutrophication of the Baltic Sea. And as a result, there was an expansion of the hypoxic zone. So what you can see here, actually in red, this is the expansion of hypoxic zones below about 80 meter water depth, especially in the central deep basins here. It was a situation in 2010. And if you look at the time series of the expansion of this hypoxic area in the central Baltic Sea, since 1900, you see that since the 1950, there is really a significant increase in this the size of this hypoxic area. Okay, so it was kind of a small introduction to the Baltic Sea system. So in 2018, in December, we had an expedition on this research vessel here, this Elizabeth Manborghese, which is actually, I would say, related to our institute, to the IOW. We took this multi-core here with us, and we recovered a core in the central Baltic Sea here, this East Coastland Basin, at a water depth of about 240 meters. And this is the core that we recovered, so it's a short core, it's just 45 centimeters. And you see that around 27 centimeters, there is strong change in the color of the sediment, as well as in the density as shown here from the X-ray radiography picture. So there's a clear change in the lithology. Okay, so I will quickly explain how we have dated the core, because it's a critical or important point for the SGSSP candidate. So we didn't use this lead 210 method to date the sediment, because as you can see here, there is actually no constant increase or decrease, depending how you look at it, in this 210. So what we do, and we have been doing it already since a few years now, we are using a so-called event stratigraphy approach to date the recent sediment of the Baltic Sea, especially in the central deep basin. So in our case, we use 3 different parameters here. So the lead isotope, stable isotope, 206 over 207, the mercury, as well as this PAH. So Neil talked about this morning, these polycyclic aromatic hydrocarbons. And as you can see that all of them starts to increase around 40 centimeter. And we think that it's the moment that actually we can see the trace, so to say, of the beginning of the second industrial revolution, or technological revolution. So we assign here the date of 1870 plus minus 10 years with relatively large error bars. So this is our first time event, so to say. Second one, we use here the appearance and abrupt increase of DDT pesticides in 1950. So relates to the beginning of the usage of DDT for agriculture. And here we have also another argument to put here 1950. We can talk about this at the end of the presentation. The next tool we use to date the data, it's more a local tool, I would say. So we looked at this increase in the manganese, titanium, and cobalt aluminum ratios here. Related to actually the so-called major Baltic inflows, or MBIs. So what are these MBIs? Occasionally, I would say, actually there's the input or inflow of salty and oxygen-rich North Sea water here, entering the Western Baltic Sea at depth, and then reaching the Central Baltic Sea. And when this oxygen-rich water enter into the sulfidic water of the deep water of the basins, then this manganese carbonates precipitate. So we are lucky to have extremely nice monitoring data in the Baltic Sea. And here what you can see are the content of oxygen in the water column below 230 meter in the East Coastland Basin, so really where the core was taken since 1960. And you can see here this event, I would say, we bring a lot of oxygen into the deep water of the Baltic Sea. So these are these inflowing events. So we use them actually and correlated them to our manganese, titanium, and cobalt, aluminium peaks. Okay, so by this way we can put some different timers, time event, yeah, between 1964 and 2014. Okay, so and the last tool we used to date the core was this increase in cesium-137, which is related to the Chernobyl accident in 1986. But at the end, this is what we have, this is our age model. So to date the deepest part of the core, we just extrapolated and we get an age of 1840. And for the uppermost sediment, we just we assigned the date 2018, so the time of the core recovery. And you can see that actually we have sedimentation rates of about 0.2 until 1950, and then they double after 1950 to about 0.4 centimeter per year. Okay, so this is for the age model, and then I will just go through different, let's say, Anthropocene markers we have been looking at. And we will always have so it's always again plotted against steps, and here next to it the equivalent ages. So first of all, the radionuclides, so the 241 americium, 239 plus 240 plutonium, and so here this ratio between 240 and 239. So basically Andy showed this slide before, but as he said, we can see that at the very first time that we can detect actually plutonium, apparently there is the source was more the Pacific proving grounds, and shortly after we enter, so to say, into values corresponding to the global fallout. And then finally here we have the, on the right, we have the fractional C14. So it seems that there is a first increase at 27.3 centimeters, so dated 1953, for at least for americium and plutonium. Seems to be maybe a little bit later for the radiocarbon, so 26.5 centimeter, dated 1956. A maximum, sorry, as expected, dated 1963, so it seems that our age model is consistent. And again, the maximum is maybe a little bit later in the radiocarbon. Okay, then here some markers, like novel materials markers. The SCP reconstruction record, so Neil talked about it already this morning. Then we have next to it here the microplastic records. Here again, this PAH construction and the DDT that I also already showed actually. And it seemed that there is an increase or a major change at 27.3 centimeters, so dated 1953. The next set of markers are actually organic matter proxies. So from left to right, there's first total carbon, total organic carbon, total nitrogen, total organic nitrogen. So the CN ratio, and then the delta C13 of the organic carbon, so both corrected and uncorrected for the Zeus effect, and then delta 15N. And it seems that there is a major change at a bit later, 26.0, bit higher in the core, 26.5 centimeter, dated 1956, plus minus 4. We measure also trace metals, the core. So here I put the one that should have a kind of a anthropogenic origin. And so on the left is mercury, then there's copper, zinc, lead, and again, these lead stable isotopes. And here it seems that the first change may be even a little bit earlier, around 28.8 centimeter, dated 1947. But I think we have to be careful with trace metals because they are redox sensitive. So in settings such as the Baltic Sea, it can be a little bit tricky maybe. Okay. And then the last set of markers, these are biomarkers actually. So basically lipids which are preserved in the sediments. The first one here on the left is brassicastherol, which is actually derived from diatoms, so phytoplankton's primary production. So it would be a marker for eutrophication. The second is tetrahymanol. So this is actually derived from ciliates, which are, let's say, zooplankton. And actually, this is more proxy showing the development of the redox line in the Baltic Sea. The green curve is proprostanol and epicoprostanol. So these are actually derived from fecal matter. And this R2 ratio here in orange, as you can see, actually indicate that these fecal lipids are mainly derived from humans. Okay, and then here again, it seems that there is a main change in the appearance of this coprostanol and epicoprostanol at 26.5 centimeters, so dated 1956. Okay, so basically I went through the most of the markers and took kind of summary. So we also think that the primary markers, as primary markers, the americium 241 and plutonium 239 plus 240. And what we did actually is to be a bit more objective. We applied a change point model to try to see at which moment is the main change in these proxies. And this model suggests that the main change occurred here at 26.5 centimeters to 1956. And as you can see here on the left, is actually nicely also corresponds to this transition in the lithology of the core. And then here's some of the secondary markers that we proposed: the ACPs, the DDTs, TOC, then the delta C13 of the organic carbon. And again here on the right, a close up on the near the transition, where we can see the changes in the color of the sediment. So we actually propose that this 26.5 centimeter dated 1956 as a GSSP level for the Baltic Sea. Yeah, I mean, actually, I'm already done. Thank you very much for your attention.
Thank you, Jerome. Do we have any questions from the floor, first of all? And how about online? Anything coming through? Oops. Oh.
Juliana.
I'm sorry, I can't see the question.
Yes.
Shall I?
Question. Just congratulations, Jerome. Sorry for his presentation.
Okay.
Can I have a question?
Oh, yes. Okay, so we have a question from Yoshi. Do you want to give the question yourself, Yoshi?
Yeah. So it's a wonderful data set. So thank you very much. So I have two questions.
Right.
One is the sedimentation rate is very low in 1950s. So what is the controlling factors?
There's an increase around 1950.
1950 is the lowest.
It's not the lowest. I mean, it's until 1950. Okay, it's like about 0.2 centimeter a year, and after 1950 there is a change. Okay, going then up to about 0.4 centimeter per year. But 1950 is not especially low.
Yeah, and the second one is photos. Show the last photo, you show the core photo, show the 25 to 20 centimeters. There are some trace fossils. And
do you see my presentation still, or?
The last, I mean, the two from the last.
Here?
Yeah, around, yeah.
Yeah.
25 to 20 centimeters, just a boundary.
Yeah.
There is some trace fossils. So
no, these are not trace fossils. These are actually these are manganese carbonate layers.
No, just a boundary, 26 to 7, around just boundary, color boundary. So you show the slide from the last two.
Oh, do you mean the biomarkers?
Second from the last.
This one?
No, more later.
Which data?
No. Not last, close to the last slide.
The last slide?
Yeah, close, yeah.
This one?
Yes. So right side 26 to 7 and 8 looks like a very small, it's a trace fossils. How about the bioturbation effect of this core? That's the question.
So before here, so this is when this basin started to be anoxic. Okay, so before there might have been some bioturbation, but as soon as this hypoxia settled, then after this there is no more bioturbation because there is no more oxygen in the basin. Yeah.
Yeah. At the 26 centimeters, there are small white spots. Looks like trace fossils. Yeah.
No, it's not. I can tell you. I mean, you cannot see it exactly on this. This is just a zoom. I mean, on the core. But if you look really into details, it's not. It started to be this moment that the sediment started to change into a much more organic-rich sediment.
Okay. Thank you very much.
Thanks for your question. I don't see if there are any other questions.
Yep. There you go. There is a query, not from here, but obviously you have a laminated succession. Why do you think they're not valves?
Because there is no, I mean, the Baltic Sea is a complex system, and there is no real mechanism that would allow us to think that these are valves. I mean, there are some years, for example, you have really huge blooms of phytoplankton, of cyanobacteria, so it's going to be maybe preserved. And the year after, maybe you don't have so much of this phytoplankton, and then you don't see anything in the sediment. So you don't have, it's not regular like in a lake, yeah, where you always have the same things going on. So and then that's why, and then there were also some people who try to look at sediment into details, not only here at this moment, but also in the Holocene thermal optimum. There are also some laminations, and it has been shown that they are not comparable to valves.
So in places like the Gulf of Mexico, where the hypoxia is seasonal, presumably there is the potential for valves to be developed. But in your case, when it goes hypoxic, it stays hypoxic.
Yeah.
Okay.
Yeah.
Okay. Thank you very much, Jerome. I think we have to go on to the next presentation. But
yeah,
very well presented.
Welcome.
Thank you.
Okay.
So, our third presentation is in person. So we have Francine McCarthy from Brock University, who will be presenting on the Crawford Lake succession in Canada.
That'll work. I'm going to talk to you today about a site in Canada, in a rural area in the drainage basin or catchment of Lake Ontario. It's about 50 kilometers west of Toronto, and it's about 30 kilometers northeast of an industrial city called Hamilton, Ontario, which is a very large steel town, and that's going to become important to the story. The lake...
Sorry, we can't see the slide. Or at least I can't see it.
Okay, thank you.
We cannot see, I cannot see it either.
Thank you. I don't need the mouse. Can you see the slide now?
Not yet. Okay, good. It's coming. Yes.
Good. Excellent. So as you can see, the lake is in a conservation area. The land was sold to Conservation Halton in 1969 to preserve this lake, which was known to be meromictic, doesn't fully mix to the bottom. And that was a very important decision because there were developers who were interested in buying the land to put some housing complexes on it. So, this is not. Oh, so as I said, it is just northeast in a rural area, but northeast in a prevailing wind direction from this steel town, and so that's important. The most popular attraction for the conservation area is the reconstructed village of indigenous longhouses. And you can see on the right the interior of a longhouse. These were Iroquoian language people who were cultivating crops, the maize, corn, and beans that were the Three Sisters, as well as sunflowers and other crops, as well as some hunting to supplement their diet. And in May at Hakave, I communicated with a descendant of the people who built these longhouses and occupied the settlement for a 218-year period between the late 13th and latest 15th century. And she is an artist named Catherine Tamaro, and so we had this conversation across the globe, so to speak. And she's sitting in a longhouse with a piece of art that she had done. So here you can see a reconstructed longhouse. There were up to 6 at any given time over that 218-year period with the crops that they cultivated. And the fact that these indigenous people cleared land, mostly by slash and burn, and tilled this land over 218 years, which we know because we have true varves and we know exactly how they form, so we can count the varves. So that they impacted the lake. And then, for some reason, they left the site, and all of the other settlements by these people were abandoned simultaneously in the late 15th, earliest 16th century. And the lake was not affected by people until 1843, when the deed to the land was given by the British Crown to the Crawfords, and they then built a lumber mill. So there was a large impact in the Industrial Revolution. So the question is, was there an impact in the mid-20th century? And there was a former professor of biology at Brock University, where Martin and I work, who studied this lake limnologically for several years with his graduate students. And in a gravity core, not in a freeze core, but in a gravity core, they managed to see the varves well enough that they were confident that to date a major assemblage change in chrysophytes at 1954. And they also see in the bottom inset there, if you can see it, it's pigment data, and you see a major change in the pigments around the same time. So the question then is, can we see a change in the mid-1950s? And in fact, we can. You'll see in many of my diagrams the indigenous interval as well as the European colonists, and then ultimately the Canadian zone and what we're calling the Anthropocene, which in this slide that just came up is, a figure that just came up is in the dark gray. And you'll see that there are great similarities between the indigenous interval and the colonial Canadian interval. this is human impact at a local scale. But what we see in the last 70 years or so is a different kind of impact. So I think one of the values of this site, which has many interpretive facilities, a boardwalk around the lake, and, an interpretive center, the longhouses have guides and interpretations and so on, is that it really brings across the difference between anthropogenic impact, which is a local scale and therefore hugely diachronous, and what I realized when I had the honor to co-deliver a speech with Jan Zalazevich at the IGC not long ago, and I looked at all of the different sites that we are examining as potential GSSPs, and no matter what kind of Earth system you look at, there is a response of the world to something that happened in the mid-20th century. And that is, to me, a very powerful message. So lakes are great places to do recent paleo-ecological investigations because they really, really capture anthropogenic things because they are in the midst of continents where a lot of the activity happens. And particularly in meromictic lakes, you have the opportunity of having annual precision. And this is what you can see in the photographs of two different cores where the layers are annual, dark colors in the winter, light colors in the summer, which I'll describe more in a little bit. And like tree rings, we can count them to get very, very precise varve chronology. And they are undisturbed, except occasionally by what are, the circle one here, can't really deal with it, but there are occasional goose droppings in cores that will depress the varves, but that's very rare. Otherwise, they are undisturbed. In my talk, I will tell you a fair bit about the lake itself, what makes the varves accumulate the way they do, and quickly at the end, I'll run through some of the core data, because we also have a poster on the core data, so I'll tell you more about the system itself. And in order to have a geological record of the Anthropocene, that we can have a hope of predicting what will happen in the future, which is what a lot of people ask about, is how do you know what's going to happen in the future? You have to really understand the geologic system, the depositional system that you're dealing with. So here we have a small lake in a rural area that has a very deep basin. It is a sinkhole that developed in the dolomitic limestones of Silurian age of the Niagara Escarpment, the same rocks that Niagara Falls flows over, near where Martin and I work. And in this area, it's separated from most of, sort of an outlier of the escarpment by a small valley, and that's important because it's in that small valley of Limestone Creek at Nasagoya Canyon. You see it on the bottom right diagram. You see a block diagram in the top right. That's where the water enters the aquifers, the highly porous and permeable layers of the dolomitic limestone in this karstic area. And these highly transmissive groundwater flow zones transect the basin. And this is a critical reason why the varves form the way they do in Crawford Lake. And this was postulated before the last 4 years when my students and I did a lot of work to figure this out, but we now can prove, we have evidence for how this works. And this little cartoon just shows you the location of the indigenous village, the very, very deep relative to the size of the lake, which is what inhibits the full mixing of the water, what develops the meromixis, and the groundwater that's, of course, in this karstic limestone region, very, very rich in calcium and carbonate and bicarbonate ions and so on. So as I said, we did a lot of work to characterize not only the lake, but the catchment of the lake, the groundwaters seeping out of the springs, the bedrock, and so on, and the water column of the lake. So it's at its maximum, it's 24 meters deep. And so, at least in every season, we have multiple readings over the 4-year period of temperature, salinity or conductivity, electrical conductivity, dissolved oxygen, and pH. And it's a very unusual meromictic lake. So typical meromictic lake doesn't mix. The temperatures are very, very constant in the monomolymnion, the not mixed layer, whereas in the mixed layer there is a thermocline that develops through the year. But in Crawford Lake, we see this. The darkest gray is always going to be the monomolymnion. So the monomolymnion, much, much, much higher electrical conductivity, very low, surprisingly low pH. So it's actually slightly acidic in the bottom, which is very strange, but it's never anoxic. It's never anoxic. That in C, the dissolved oxygen, the line is the limit of hypoxia, never gets close. And so the reason for that, of course, is the groundwater that's recharged less than a kilometer away still has a lot of oxygen dissolved in it, and it has a lot of ions dissolved in it, which gives it the conductivity. So we fully understand this system. In addition to physical measurements of the properties, we did chemical analyses. You can see the difference. As soon as you cross the chemocline, the boundary between the mixolimnion and the monomolymnion, you see the much higher concentration of dissolved inorganic carbon, organic carbon, all the ions. You can see the salinity in the water. And this is what inhibits bioturbation. It is not anoxia, it is the slightly saline conditions that, so I can't get into it because it'll take too long. So because of that, there are microinvertebrate animals, cladocerans, rotifers, who deliberately go into the monomolymnion during the winter where it's relatively warm. There's lots to eat, lots of detritus, lots of inorganic, or lots of organic carbon, I should say, lots to subsist on until the conditions are right again and the phytoplankton grow and they go back to being grazers. But in the winters, it's their Florida. So by looking at the lake over the 4 years that we examined it, and we deployed sediment traps. We deployed one trap at the base of the epilimnion, the surface layer, and one at the chemocline. And we collected these traps 3 times, the contents of the traps, so that we could capture fall turnover, spring turnover, and the summer. There are logistical reasons in Canada why capturing things in the winter is difficult in terms of weather, and we were hit by COVID every winter of our investigation, so we were very limited in what we could do. So I will just show you very quickly the results of the sediment traps, the top trap and the bottom trap. And that bottom trap at the chemocline, the sample we took in mid-October, which is right when turnover has happened, fall turnover. So the surface water gets cold, the day length is less, most of the phytoplankton die, sink to the bottom, and that's what makes the organic layer, the dark layer of the varves. It mostly accumulates during fall turnover, and then it continues to accumulate between fall and the next spring, that June 21st interval. And there's very little organic matter that reaches the lake bed in the summer. So between June and September, very little organic matter, but lots and lots and lots of calcite. And the calcite crystals, they nucleate in the surface waters, the upper 6 meters, when the temperature is warmer than 15 degrees Celsius and the pH is higher than 7.8. So quite basic, quite warm. All of those calcium and bicarbonate ions precipitate calcium carbonate. And they're little tiny crystals in the surface, and they sink, and we found them in the sediment trap, lots and lots and lots of small crystals of calcite in the summer. And those that weren't caught by our sediment trap, they continue to sink to the bottom trap where they reach density contrast at the chemocline, and they sit there when they encounter this water that's much, much richer in calcium and carbonate ions, the high conductivity, and it's a little bit acidic, and that combination causes them to grow. And they grow until they get large enough to overcome Stokes' law, and they sink rather quickly to the bottom, where, of course, they're being dissolved a little bit because the water's a little bit acidic, but enough of them accumulate so that it makes a white layer. And that's what we know. Every summer, we have this layer that caps the organic matter that accumulates the rest of the season, and it's mostly, the dark layer is mostly authigenic phytoplankton and their consumers, and we know that to be the case. We did, everything from radiocarbon analysis to everything tells us that it's mostly stuff that is taking the carbon from the Silurian bedrock as opposed to a lot of the carbon from the air. So if you want radiocarbon ages, true radiocarbon ages, you have to only measure it from upland plant macrofossils. So super quickly, because you'll see this in the poster, we did lots of field work, collected lots of cores, and that was captured by by Mercury Films in a documentary, short documentary. And this is what our cores look like. Light and dark, light and dark, light and dark every year, just like tree rings. But you see that there are specific patterns. They're not just equally light and dark. There are times when you have thicker varves, thinner varves. There are intervals like the one that the blue line is matching where you have a large interval, well, a centimeter thick interval where the light lamina are very hard to see. And they're separated from another of these dark centimeter thick layer by three very, very clear, a triplet, I call them, of clear white lamina. Those clear white lamina were deposited in 1956, 57, 58. So if you want to find any year at all, you just count, the layers from there or from anywhere because we have a very reliable varve chronology. The very thick white lamina there was deposited in 1935 in the midst of the Dust Bowl in North America. So we can correlate these between core to core. Any freeze core you bring me, I can just point exactly to the to the right layer. And we did ultra high resolution imagery to double check or to develop this varve chronology. This is a system that was used at Carleton. And this was hanging at HKV in the foyer. And you can see just how crisp these varves are. The triplet is just to the left of the two panels, the split between the two panels, and the dark layer below, the dark layer above. And this makes the boundary between what we're calling the Holocene and the Anthropocene, right where the panels break. Well, it's not just a fluke. We chose those for the display. You can even see the little crystals of calcite that have sloughed off, dried off the core. So this is how distinct our varves are. And in terms of the core record, as I said, you'll see them on the poster, but this is what the steel city of Hamilton looks like. Lots and lots of steel mills, critically burning lots and lots of coal, coking coal, which is an integral part of the steelmaking industry. The spheroidal carbonaceous particles that Neil told us about this morning, huge numbers, end up in Crawford Lake. Andy was telling us about the plutonium signature. That's the plutonium signature from Crawford Lake up above. You see a clear inflection between the sample at 1950 and the one at 1954 in terms of the spheroidal carbonaceous particles. Again, you see a very clear inflection around 1952. So we propose putting the base of the Anthropocene at the white layer, the summer layer of 1952 in the cores. Oh, and the grain size of the spheroidal carbonaceous particles, you can see the smallest grain sizes that are on the left, the yellow and the blue, they become abundant in the Anthropocene, whereas the coarse grain sizes are abundant farther down. Now remember, there was a lumber mill where they did a lot of burning, and so that's not at all surprising that this is the pattern that we see in grain size. It's a good thing that grain size was done on these spheroidal carbonaceous particles, isn't it, Simon? So we also see a major change in microfossil assemblages. So here's an example of diatoms and of chrysophytes, this two siliceous microfossil types. And so in the top diagram, it is from 1930-ish to 1979, and you can see that the constrained cluster analysis picks out a major assemblage break at 1952. And in a longer record, where we have slightly lower resolution through the early 1900s and the latter part of the century, you can see that major assemblage break really clearly. And the siliceous microfossils, both the diatoms and the chrysophytes that become abundant in the 1950s, 60s, are taxa that like less alkaline, more acidic, and water clarity, very clear water. And if you have all of this industrial activity pumping out, combusting fossil fuels, acid precipitation along the catchment, you're going to, even in this very well buffered limestone basin, you're going to see an effect. And in fact, you're going to reduce the amount of time over the summer season that calcite can precipitate. And that's why you have the dark layers in the 1950s and 60s, except for that little triplet that I mentioned. And that's why you have the water clarity, because it's in the summer month that these things are mostly growing. And the calcite is a very good little prism to capture light and send it back to space. But if you reduce the amount of calcite, you increase the clarity of the water. And so it all makes perfect sense, but it takes an awful lot of effort to get to the data and interpret them to the point that you can just tell the story like it just kind of happened. But so here's more evidence to support the idea of acid precipitation, starting in the 1940s, but really between the 40s and the 70s, bringing a lot of terrigenous elements into the lake. And those terrigenous elements like titanium, potassium, and so on, incorporated into the bodies of the phytoplankton and the zooplankton and so on, and accumulating on the lake bed. So that we expected when we did the iTrax analysis to see, because it was at 200 micrometers, so it was really high resolution record, we thought we could see VARV scale resolution. Well, we can't quite, but what we do see is you can pick out that triplet of VARVs, both in the RGB scan that iTrax produces and in the core photo that I superimposed on the left. And you can see that interval of the darker colored intervals of the core with the thin summer lamina that correspond with the phytoplankton who like slightly acidic conditions. And I put these photos here just so that you can see how thin a rind we collect on these freeze cores. So this means that in order to get enough material for analysis, you really need to do an awful lot of work if you're trying to get like annual scale resolution, because annual scale is like a millimeter thick. But you can do it, it just takes a lot of effort and it takes a lot of core. So by the time we had done all of the analyses that needed to be done for the AWG and for our purposes, we had no core left to be the GSSP. So I'll tell you that in a second, but the GSSP, so we went back out this winter and we took a core that is currently, like literally currently being analyzed for a huge slew of Anthropocene markers, including POPs that we hadn't had the opportunity to analyze before. But this is a core that I'd had in my freezer since 2011, And you'll see the data on the wall in the poster session, but the SCP concentrations increase, the fraction of radiocarbon, I should say, increases in the early Anthropocene. The percentage of elm pollen, ulmus, declines because Dutch elm disease decimated elm trees in North America. And you can see that the increase in titanium. So that's the core that we collected, and we did that in collaboration with our indigenous partners at the site. So you might see some cedar boughs at the bottom left where the photograph of the new baby core is being taken because there was a ceremonial aspect to the healing of our activities at the lake associated with that. One of the complexities of working respectfully in these kinds of systems. And so that's what the freeze core looks like that's now at the National Cryobank in Ottawa, at our national capital, at the Canadian Museum of Nature. And you can see the white layers at the base of the indigenous zone. That was during the medieval thermal optimum when the occupation of the site, the land clearing for the site, and the cultivation of the crops increased the number of the nutrient influx to the lake, which allowed lots of productivity, lots of primary production, which tied up carbon, which increased the pH, made it more alkaline, allowed for the calcite to precipitate. So since through the indigenous interval, there are annual varves, and through the European interval, there are annual varves. We now know that in between, during the Little Ice Age, varving wasn't annual. The calcite didn't precipitate every single summer. There are some white layers, but they don't add up to the right number, and we know from transfer functions of pollen data and so on that the temperatures would have been very marginal at any point for there to be precipitation of calcite. So we didn't just take freeze cores, although they're the best. We also took gravity cores and push cores to get enough material to work with because we just didn't have enough mud. And we analyzed these at lower resolution, lower temporal resolution, but over a longer period of time. And the disappearance of okanone, which is pigment produced by obligate anaerobic purple sulfur bacteria, that the stipple identifies the indigenous zone, and it disappears at the same time that they abandon the village. So since the late 15th century, the lake has been well oxygenated to the bottom. But before then, it was anoxic. And okay, so you might think, well, that's one core, that's just a fluke. Well, we had actually analyzed previously a core that we'd lost the Anthropocene out the top of the core, and unfortunately I couldn't turn the Excel file around to show you better, but that's the depth of the okanone on the bottom. And you can see that the okanone disappears at around 10 centimeters in that core. 10 centimeters in that core is the top of the indigenous zone. I know because I did the pollen work. That's where the cultigen pollen, like sunflower and corn, disappear. And in both cores, it's the same story. So that's what the next phase, my incoming grad student is going to be studying why this fluke happened. Is it a coincidence, or is there cause and effect? And I'm pretty sure I know the answer, but we'll have to wait a few years for him to finish his work so we can prove that. I can tell you what I think the answer is at the post-session if you want. But that's a core that we had.
Francine, is it
I'm
possible
too
to
long,
wrap
am
up?
I?
Yeah,
Okay.
if you could wrap up.
I'm done. Look, I was actually done.
Good, thank you. So we are quite a way behind schedule now, so if we could leave questions for the poster session later on. And if we can go now to our next presentation. So we have Barbara Fialkiewicz-Koziel from the Adam Mickiewicz University in Poznan, talking about the Snierskie peat succession in Poland.
So, good afternoon. So we going back to Europe, and I have a great pleasure to present my results of my study. Śnieżka peatland is an ombrotrophic type of peatland. It means that plants which form peat body receive both water and nutrients from the air. And this made this peatland a great example of peatland which record environmental alteration and atmospheric pollution. Śnieżka peatland is located in the Sudetes Mountains in Central Europe, and the core was collected from the Polish side. The peatland is located on the boundary between Poland and Czech Republic, and we, of course, take our core from Polish side. And at this moment, the most important is to mention that this peatland in this place, the westerlies dominate, and the Sudetes are characterized by high precipitation, around 1,500 millimeters. It is twice higher than the rest of Central Europe. Śnieżka peatland is located on a plateau close to the highest summit on the Sudetes. And very quick look on Google Earth. Here is our peatland and the distance to the summit. So different perspective. Okay, so we collected 3 cores. 2 of them were retrieved in 2012, SN1 and SN2. Using water core, which is visible on this picture. And the third one, because of keeping the stratigraphic completeness across the GSSP level, was collected in 2020 and only partially subsampled for complementary analysis. Some pictures of coring. So after coring, we wrapped our core into plastic and put to this box to avoid any disturbances during traveling back. In the laboratory, this peat core was sampled using procedure proposed by Givela et al. So we sliced our profile into 1 centimeter slices, and every slice was dated using different methods and analyzed. And as I told you, the SN0 profile, which is our GSSP candidate, was only partially subsampled. Before any interpretation of peat profile, the most critical step SN1, which is the most detailed profile, was also dated using Litho-10 and C14 and compare with cesium and plutonium. I also show some results of SN2 to show the similarity between 3 profiles. So this picture shows the relation between plutonium, cesium, and obtained Litho-10 HDF model. So first conclusion is that we have very similar shape, the pattern of plutonium distribution in SN0 and SN1, what means that we have that plutonium is immobile in peat profile. In case of cesium, we observe more complex pattern of distribution. There are some differences between 2 cores. It is due to a partial mobility of cesium. However, we were able to distinguish some important signals linked to Chernobyl accident and also in the case of SN0 to nuclear weapon tests. While the maximum of plutonium fit pretty well with obtained HDEF model, it is important to explain some discrepancy between first maximum of plutonium and obtained HDEF model. It is because lead-210, the model obtained from lead-210 have greater uncertainty with DEF. So it's not because of mobility. Plutonium first maximum is dated on 1952, and in our opinion, plutonium is more reliable than lead. We also perform some geochemical analysis to determine the level of anthropogenic impact. So we measure trace and rare earth elements in SN1 and SN2, as well as lead isotopes to distinguish possible sources of our pollution. And mineralogy using scanning microscopy was determined in all three cores. And before showing you this graph, I would like to pay your attention on three types of technofossils. Neil, in morning session, told you about STP, and there was a talk, the discussion about inorganic particulates. So we measure spheroidal aluminosilicates. It's an amorphic part of inorganic part of peatland, and we measure crystalline phase mullite, which is also a product of coal combustion, high temperature coal combustion. And also we determine the occurrence of STP. So SN1 and SN2 spans more or less 200 years. So we also observe some older dates, but maybe we don't have time now to explain why I have different time. If you want to know more, I think maybe during poster session I will explain more. But what we can see, we can observe some increases in trace elements linked to industrial activity. Śnieżka peatland is located in a very special place because it's surrounded by Poland, Germany, and Czech Republic. And in 1970s, this tree neighboring country caused a dramatic pollution in this area. But what can distinguish this picture into two phases, one before 1950 and one after 1950, is appearance of our technofossils. Look here, we have mullite, and the same is in SN2. Also, appearance of CAP, here only mentioned as a presence or absence. So this line shows us the first presence of CAPs. And the black line shows first maximum of plutonium global fallout. In case of SN2, we didn't measure plutonium. In terms of biostratigraphy, based on pollen analysis, we could find some regional trends linked to agriculture and pasture. But what is the most important in terms of global comparison of biostratigraphic markers is appearance of ambrosia anthemicifolia. Here, it is invasive, non-native for European country plant, and its first appearance was dated in 1956. It is comparable to historical sources from literature. We also investigate the state amoebae. The state amoebae are very interesting microbes. They are very important microbial community in peatland, and because their ecology is well known, they are used to establish some ecological alterations, some changes. And they are great markers of hydroclimatic changes. And we found that in 1960s, there's an absence of very sensitive mixotrophs, which can be attributed to climatic changes. It is also linked with the increase in temperature, global increase in temperature, and decrease in precipitation. In the same time, we observed the increase other more resistant species of the state amoebae. Among them, we found species which can build their shell and use fly ash to build their shell. So this is a very interesting microfossil. Okay, so summarizing, I made my summary using two profiles, SN0, which is our proposed GSSP level, and SN1. And we can observe the great similarity between both profiles. We use plutonium, as it was explained in morning session, as a primary marker because it's the best preserved radionuclide in peatland. And the first appearance of plutonium is supported by appearance of technofossils like mullite, spheroidal aluminosilicates, and STPs. We also observed a dramatic upturn in trace elements like mercury, but also lead and zinc, but also aluminium. We observed a change in isotopic signature of nitrogen, which can be compared with, it's not visible, but you have to believe me. We observe here the increase in urtica pollen, abundance of urtica pollen, which is a good indicator of nitrogen. We also observed the absence of climatically sensitive species. Śnieżka peatland is important for Anthropocene discussion because it is a great archive of changes which are synchronous with other parts of the Earth, like plutonium global fallout, release of artificial radionuclides, appearance of technofossils linked to high temperature coal combustion, and pronounced inflection in metals linked to industrial activity. We also observe climatic changes linked to global warming, as well as the appearance of non-native invasive plants. This site has some advantages and disadvantages. It displays a robust age-depth model which gives us quite high this profile is characterized by a relatively high peat accumulation rate. So in 1 centimeter, we have around 2 years of accumulation, and this provides a high resolution geological record and can be used for distinguishing boundary between Holocene and Anthropocene. And this profile encompasses a wide array of critical markers mentioned before. Śnieżka peatland is located in the national park, and this access to the peatland is facilitated thanks to proximity to touristic tracks. It also has some disadvantages because we don't have such beautiful lamination like in case of lakes, and there is a lack of lithological marker at the proposed level, so we need to base our analysis on good age-depth model. But peatland provides a lot of organic material, so it's a good material for C14 dating and lead-210. Okay, thank you very much.
Thank you.